The moment the first full-color images from the James Webb Space Telescope were released in July 2022, astronomers around the world realized they were looking at something profoundly unexpected. The images were not simply sharper or deeper than anything before them. They revealed objects that appeared to violate long-standing assumptions about how quickly the universe could form complex structures. Within hours of the public release, researchers from institutions such as NASA, the European Space Agency, the Space Telescope Science Institute, and universities across the United States, Europe, and Asia began circulating preliminary analyses that carried an unusual tone. Instead of cautious optimism, many reactions included words like puzzling, confusing, and hard to reconcile. If the early universe has ever captured your imagination, the James Webb Space Telescope offers a new perspective. Subscribe now to follow the discoveries. Its first images suggest a cosmic history richer and more complex than astronomers once believed. The image that triggered the strongest reaction was the first deep field observation, known as Webb's first deep field, centered on the galaxy cluster SMACS 0723. This cluster, located about 4.6 billion light-years from Earth, was selected deliberately because of its gravitational lensing power. The immense mass of the cluster bends space-time, magnifying and distorting the light of galaxies far behind it. Webb observed this region for just over 12 hours, a remarkably short exposure compared to the days or weeks required for similar deep-field images from the Hubble Space Telescope. Despite the brief observation time, the image revealed thousands of galaxies, some appearing as faint smudges and others as elongated arcs caused by lensing effects. What immediately stood out was not just the sheer number of galaxies, but their apparent maturity. Several objects showed brightness levels and color profiles consistent with substantial stellar populations. According to standard cosmological models, galaxies in the first few 100 million years after the Big Bang should have been small, irregular, and dominated by short-lived bursts of star formation. Instead, Webb's images suggested the presence of systems that looked surprisingly large, compact, and organized, hinting at a level of development that should have required much more time. The James Webb Space Telescope, launched on the 25th of December 2021 aboard an Ariane 5 rocket from French Guiana, had been designed precisely to explore this early period of cosmic history. Its primary mirror spans 6.5 meters and consists of 18 hexagonal segments coated with a thin layer of gold to optimize infrared reflectivity. Webb operates at temperatures below -220 degrees Celsius, allowing its instruments to detect extremely faint infrared signals. Positioned nearly 1.5 million kilometers from Earth at the second Lagrange point, the telescope maintains a stable thermal environment and uninterrupted view of deep space. Within days of the image release, teams led by researchers such as Rohan Naidu at the Harvard-Smithsonian Center for Astrophysics, Ivo Labe at Swinburne University of Technology, and Erica Nelson at the University of Colorado began identifying candidate galaxies with estimated redshifts greater than 10. Redshift is a measure of how much the universe has expanded since the light left a distant object. A redshift of 10 corresponds to a time when the universe was roughly 480 million years old, while redshifts above 13 push observations into the first 300 million years after the Big Bang. These early estimates were based primarily on photometric data, meaning that astronomers inferred distances by analyzing how bright galaxies appeared across different infrared filters. Even with this limitation, the implications were striking. Some of the brightest candidates appeared to be far too luminous to fit comfortably within existing models of early galaxy formation. Follow-up analyses quickly began to test whether dust, unusual star populations, or lensing magnification could explain the apparent brightness. The surprise intensified when preliminary stellar mass estimates were calculated. Using data from Webb's near-infrared camera and models of stellar populations, some galaxies appeared to contain billions of solar masses worth of stars. One object, later referred to informally as Maisie's galaxy, seemed to have formed when the universe was only about 390 million years old. Another set of galaxies, identified in the CEER's survey, appeared to approach or exceed 1/10 the mass of the Milky Way, while existing less than 700 million years after cosmic dawn. Before Webb, astronomers believed that assembling such massive systems would require far more time. Computer simulations based on the lambda cold dark matter framework predicted that galaxies grew through hierarchical merging, starting from small dark matter halos that gradually accumulated gas and stars. In these models, the earliest galaxies were expected to be faint and difficult to detect, not prominent and abundant. Webb's observations suggested either that galaxies formed stars far more efficiently than expected, or that current models underestimated how quickly matter could collapse into dense structures. The reaction from the scientific community was immediate and intense. Private discussion forums, conference calls, and email chains filled with rapid interpretations and debates. Within weeks, dozens of papers appeared on the RxIV preprint server, many openly acknowledging tension between the new observations and long-standing theoretical predictions. Some researchers emphasized the need for spectroscopic confirmation, which would provide more precise distance measurements, while others argued that even conservative assumptions failed to eliminate the discrepancy. NASA officials were careful in their public messaging, emphasizing that Webb was performing exactly as designed and that surprising discoveries were part of the mission's purpose. Thomas Zurbuchen, who served as NASA's Associate Administrator for Science at the time, described the images as an invitation to explore unfamiliar territory. Internally, however, many astronomers admitted that the scale of the challenge was greater than anticipated for such early observations. Part of what made the situation unusual was the speed at which Webb's data forced reconsideration of assumptions. Hubble's deep field images, such as the Hubble Ultra Deep Field released in 2004, took years to fully analyze and interpret. Webb's first deep field image triggered substantial debate within days. The telescope's sensitivity allowed astronomers to detect galaxies nearly 10 times fainter than those seen by Hubble at comparable wavelengths, dramatically expanding the observable population of early universe objects in a single release. The shock was not limited to professional researchers. Science educators and communicators quickly recognized that Webb's findings could complicate simplified narratives about cosmic history. Timelines that depicted a slow, incremental build-up of galaxies suddenly appeared incomplete. While no serious scientist suggested abandoning the Big Bang framework, the details of what occurred in the universe's first few 100 million years were clearly under renewed scrutiny. Another factor amplifying the reaction was the consistency of the anomalies across different observing programs. Similar early massive galaxy candidates were identified in Webb's observations of multiple fields, including the Cosmic Evolution Early Release Science Survey, and later the JWST Advanced Deep Extragalactic Survey. The repeated appearance of these objects across independent datasets reduced the likelihood that the findings were due to random noise or unusual selection effects. By the end of 2022, it was clear that Webb had not merely extended previous observations, but had opened an entirely new observational window. The phrase, "something that should have been impossible," began appearing not as sensationalism, but as shorthand for a genuine scientific problem. Researchers stressed that impossible meant incompatible with existing expectations, not a violation of physical laws. What made the situation particularly compelling was the quality of the data itself. Webb's images showed exceptional clarity, low background noise, and stable instrument performance. Extensive calibration checks revealed no obvious errors that could account for the unexpected results. With instrumental explanations largely ruled out, attention shifted firmly toward interpretation and theory. As astronomers continued to analyze the first images in greater detail, ongoing studies focused on refining distance measurements, improving stellar mass estimates, and comparing results against updated simulations. The initial deep-field image became a reference dataset for follow-up observations and theoretical work aimed at understanding how early galaxies accumulated mass and formed stars within the universe's first several hundred million years. How James Webb sees what Hubble never could. To understand why the James Webb Space Telescope revealed objects that earlier observatories missed, it is necessary to examine how Webb collects and interprets light in fundamentally different ways. The surprise described previously was not caused by chance or luck. It was the direct result of design choices made decades earlier, when engineers and astronomers anticipated the need to observe the universe at wavelengths that traditional optical telescopes could not effectively access. The key difference lies in infrared sensitivity. As the universe expands, light travelling across billions of light years becomes stretched to longer wavelengths. Radiation originally emitted in ultraviolet or visible light by early stars arrives at Earth as infrared light. Earlier observatories, including Hubble, were limited in how deeply they could probe this regime. Although Hubble carried infrared instruments, they were constrained by detector sensitivity, mirror size, and thermal noise. Webb was built to overcome all three limitations simultaneously. Webb's instruments operate primarily in the near and mid-infrared range, spanning wavelengths from about 0.6 to 28 microns. This range is critical for detecting the faint glow of ancient galaxies whose light has been travelling since the universe was only a few 100 million years old. The telescope's near-infrared camera captures high-resolution images across multiple filters, allowing astronomers to measure how galaxy brightness changes with wavelength. These subtle colour variations are essential for estimating distances, stellar ages, and mass distributions. The near-infrared spectrograph adds a second dimension to Webb's capabilities by splitting incoming light into its component wavelengths. Unlike imaging alone, spectroscopy reveals specific fingerprints of elements and ionized gas. Webb's spectrograph can observe hundreds of objects simultaneously using a microshutter array containing nearly 250,000 individually controllable shutters. This technology allows astronomers to target specific galaxies in crowded deep-field regions with unprecedented efficiency. Another major advance is Webb's mid-infrared instrument, which detects longer wavelength radiation emitted by warm dust and older stellar populations. This capability is particularly important for distinguishing between truly massive galaxies and those whose apparent brightness might be inflated by short-lived bursts of star formation. By sampling different infrared bands, Webb can separate light from young, hot stars and older, cooler ones, refining estimates of galaxy age and structure. Equally important is the telescope's thermal design. Infrared detectors are extremely sensitive to heat, and even small temperature fluctuations can overwhelm faint cosmic signals. Webb's sunshield, roughly the size of a tennis court, blocks heat and light from the Sun, Earth, and Moon. This passive cooling system keeps the telescope's optics at stable cryogenic temperatures, allowing detectors to operate with minimal background noise. The result is a level of sensitivity that ground-based observatories, limited by Earth's atmosphere and thermal emissions, cannot match. Webb's location in space also contributes to its performance. Orbiting far from Earth, the telescope avoids the infrared glow produced by the planet itself. This stable environment allows long, uninterrupted observations of distant fields without the periodic eclipses that affected earlier space telescopes. Over time, this stability translates into cleaner data and more reliable measurements, particularly when studying faint sources near the limits of detection. The combination of sensitivity and resolution means that Webb can detect galaxies that are both faint and compact. In earlier surveys, many early universe galaxies blended into background noise or were mistaken for foreground objects. Webb's angular resolution in the near-infrared rivals or exceeds that of Hubble in visible light, enabling astronomers to distinguish individual galaxies even when they appear extremely small in the sky. Another advantage comes from Webb's filter system. The telescope uses a carefully designed set of narrow and wideband filters that sample specific portions of the infrared spectrum. By comparing how much light passes through each filter, astronomers can identify sharp drop-offs in brightness caused by absorption from neutral hydrogen. These features provide critical clues about how far away a galaxy is and whether it formed before or during the era when the universe transitioned from opaque to transparent. This technique, often referred to as dropout selection, existed before Webb, but the telescope's sensitivity makes it far more powerful. Objects that would have been marginal detections in earlier surveys now appear clearly across multiple filters. This clarity reduces uncertainty and allows researchers to construct more detailed spectral energy distributions, which are essential for estimating stellar populations and star formation histories. Webb's detectors themselves represent another leap forward. Built using advanced mercury-cadmium telluride technology, the near-infrared detectors offer low noise, high quantum efficiency, and exceptional stability. These characteristics enable long exposure times without significant signal degradation. In practical terms, this means that Webb can accumulate light from extremely faint galaxies over hours without the data becoming unusable. The telescope's observing strategies further enhance its reach. Programs like deep field surveys combine multiple exposures taken at slightly different positions, a process known as dithering. This technique reduces detector artifacts and improves image quality. When combined with Webb's sensitivity, dithering reveals structures that would otherwise remain hidden, such as faint galaxy outskirts or subtle gravitational lensing features. Crucially, Webb was designed with flexibility in mind. Observing modes can be adjusted as new questions arise, allowing astronomers to respond rapidly to unexpected discoveries. When early images hinted at unusually massive galaxies, teams were able to schedule follow-up observations using spectroscopy and alternative filter combinations. This adaptability accelerated the pace of discovery and reduced the time between observation and interpretation. The contrast with earlier missions becomes especially clear when comparing survey efficiency. What once required weeks of observation with multiple telescopes can now be achieved in a fraction of the time with Webb alone. This efficiency enables broader surveys that sample different regions of the sky, reducing cosmic variance and improving statistical confidence. As a result, anomalies detected in one field can be tested quickly in others. The telescope's performance has also exceeded pre-launch expectations. Engineers designed Webb to meet specific sensitivity thresholds, but on-orbit measurements revealed that many instruments perform better than required. Lower than anticipated noise levels and higher throughput mean that Webb can detect even fainter objects than originally planned. These margins of improvement have direct scientific consequences, pushing observations deeper into cosmic history. What makes Webb especially powerful is not any single feature, but the way its systems work together. Large mirror size, infrared sensitivity, thermal stability, advanced detectors, and flexible observing modes form an integrated platform optimized for early universe studies. Each component amplifies the effectiveness of the others, creating a telescope capable of revealing phenomena that were previously inaccessible. By the time astronomers began to fully analyze Webb's early deep-field data, it became clear that the telescope was not merely extending existing surveys, it was redefining what could be observed at the edge of cosmic time. The galaxies that appeared too early to exist were not artifacts or illusions. They were visible because Webb was finally able to collect enough information from light that had traveled for more than 13 billion years. The combination of high sensitivity, wide infrared coverage, and stable observing conditions allowed Webb to detect early universe galaxies immediately upon operation. From its first observations, the telescope collected data in regions where prior measurements were limited or absent, providing new information about galaxy formation during the universe's first several 100 million years. Continued observations with Webb allowed astronomers to collect extended datasets probing the earliest stages of galaxy formation. The telescope's combination of infrared sensitivity, high resolution, and long exposures enabled detection of galaxies at higher redshifts than previously possible, providing new constraints for models of early galaxy assembly. Galaxies that appeared too early to exist. As James Webb continued its observations following the first deep-field images, astronomers quickly realized that they were not simply seeing distant galaxies, they were seeing galaxies that should not have existed yet. These objects were more than faint smudges on the sky. They appeared as massive, surprisingly luminous systems in an epoch when standard cosmological models predicted only small, irregular proto-galaxies. What made this discovery so striking was the combination of distance, mass, and structural maturity, all present within a universe less than 500 million years old. One of the earliest candidates identified after the release of Webb's first deep field was a galaxy catalogued as CEERS 93316, observed during the Cosmic Evolution Early Release Science Survey. Preliminary analysis suggested a redshift of approximately 16.7, which would place it just 235 million years after the Big Bang. If confirmed, this would make CEERS 93316 the most distant galaxy ever observed, exceeding previous records held by Hubble's GNZ11, which appeared at a redshift of 11.1. Spectroscopic follow-up for CEERS 93316 was ongoing, but the initial photometric data indicated a stellar mass approaching 1 billion solar masses, a remarkable figure for such an early epoch. Other galaxies soon followed. In the JADES survey, led by Erica Nelson and her team at the University of Colorado, multiple candidates were found with redshifts between 12 and 14. These objects were not only distant but bright in the near-infrared, suggesting that they contained substantial populations of stars forming at rates far higher than anticipated. For instance, one galaxy in this sample, tentatively named JADES GSZ130, appeared to form stars at approximately 30 solar masses per year. In comparison, the Milky Way forms roughly 1 solar mass per year, illustrating how extreme these early galaxies were. The size of these galaxies also presented a puzzle. Observations indicated that many had compact cores with half-light radii under 1 kiloparsec, yet their stellar mass density rivaled or exceeded that of mature galaxies in the local universe. Such a combination of mass and compactness implies highly efficient star formation processes occurring over remarkably short timescales. Simulations have predicted that assembling this much stellar material in less than 400 million years would require either extremely fast gas inflow or a significant revision of the assumptions about how quickly dark matter halos could collapse. Spectroscopy from Webb's near-infrared spectrograph began to reveal additional details about these early galaxies' composition. Strong emission lines associated with ionized oxygen and hydrogen were detected, suggesting vigorous star formation and significant chemical enrichment. The presence of these elements was unexpected at such early times because they typically accumulate over multiple generations of stellar evolution. For some galaxies, the metallicity, the proportion of elements heavier than helium, was roughly 10% of the solar value, implying that multiple cycles of massive star formation and supernova enrichment had already occurred. Interestingly, these galaxies did not appear isolated. Webb's images showed signs of clustering even in the first 400 million years, hinting that large-scale structure formation was already underway. Some candidate systems were separated by just tens of kiloparsecs in projection, suggesting that early mergers or interactions may have contributed to their rapid growth. This observation adds another layer of complexity, as hierarchical assembly models generally predict a slower build-up of structure in such an early universe. The stellar populations within these galaxies also defied expectations. Color measurements indicated a mixture of young, massive stars and older, more evolved populations. This diversity implies that star formation began extremely early, possibly within the first 100-200 million years after the Big Bang. If accurate, these galaxies began forming stars at a time when the universe was still largely neutral and opaque, a period known as the Cosmic Dark Ages. Detecting starlight from this epoch was one of Webb's primary objectives, but the apparent maturity of these systems went beyond even the most optimistic predictions. Multiple independent teams quickly confirmed similar results across different fields. Rohan Naidu's group at Harvard-Smithsonian analyzed parallel observations and identified several objects at redshifts above 13 with comparable masses and star formation rates. Ivo Labbé's team at Swinburne University cross-referenced their findings with deep Hubble data and concluded that many of the galaxies identified by Webb had simply been too faint or redshifted for Hubble to detect. The combination of Webb's superior sensitivity, infrared coverage, and resolution allowed these galaxies to emerge clearly from the cosmic background. Another intriguing aspect was the variety of morphologies. While many early galaxies appeared compact and spheroidal, others showed elongated or irregular shapes, suggesting that mergers and interactions played a significant role even at these early times. A small fraction exhibited faint, disc-like structures, challenging the expectation that ordered rotational systems required several billion years to develop. If confirmed, these disks would represent the earliest examples of dynamically settled galaxies ever observed. The discovery of these galaxies also raised questions about the role of dust. Some candidates exhibited subtle reddening, indicating the presence of interstellar dust that absorbs ultraviolet light and re-emits it in the infrared. Dust formation is typically associated with evolved stars, implying that the first generations of stars had already contributed significant material to their host galaxies. Webb's mid-infrared instrument detected faint thermal emission in some cases, providing direct evidence of this early dust content and further complicating theoretical models. As astronomers catalogued more objects, a troubling pattern emerged. The number density of these massive, high redshift galaxies appeared higher than predicted by simulations. For example, theoretical models estimated roughly 1 galaxy per cubic megaparsec at redshifts greater than 12, with masses above 10, 9 solar masses. Webb's observations, however, suggested several times that number in the observed fields, implying that early star formation and galaxy assembly were more efficient than current models could accommodate. These findings quickly led to debates within the astrophysical community. Some researchers suggested that gravitational lensing could be artificially boosting apparent brightness, but careful modelling of lensing magnification indicated that while lensing affected a few galaxies, it could not explain the abundance of massive early systems. Others questioned the photometric redshift estimates, proposing that some galaxies might be closer than initially calculated. Spectroscopic follow-ups, however, have confirmed multiple high redshift candidates, solidifying the reality of these early, massive galaxies. The implications extend beyond galaxy formation. These systems provide unique laboratories for studying reionization, the process by which the universe's neutral hydrogen became ionized by early stars and galaxies. Observing galaxies in this epoch allows astronomers to trace the timeline and efficiency of reionization, linking the emergence of luminous structures to the transformation of the intergalactic medium. Webb's ability to detect both faint galaxies and bright emission lines offers a powerful combination for probing these early cosmic processes. Webb observations identified galaxies within the first few 100 million years after the Big Bang that were massive, chemically enriched, and structurally diverse. Measurements included stellar masses, star formation rates, and metallicity levels, providing new constraints on models of early galaxy formation, star formation efficiency, and chemical enrichment. Following Webb's first round of deep field observations, astronomers collected measurable data on early galaxies, including redshifts, stellar masses, star formation rates, and structural features. These measurements revealed objects at higher redshifts and with greater mass and chemical enrichment than had been previously observed, providing datasets to inform and refine models of early galaxy formation and evolution. The redshift measurements that raised alarms. The extraordinary nature of the early galaxies detected by James Webb became even clearer when astronomers began detailed redshift measurements. It is the cornerstone of understanding just how early these galaxies were in cosmic history. For Webb, obtaining accurate redshifts required pushing the limits of both instrumentation and analysis techniques, combining multiple methods to confirm the unprecedented distances of these galaxies. Redshift occurs because light from distant objects is stretched as the universe expands. The greater the redshift, the faster an object is receding from us, and the earlier in cosmic history it existed. For the newly discovered galaxies, redshifts exceeded 12 inches in many cases, corresponding to a universe that was less than 400 million years old. CE EARS 93316, for example, initially estimated at a redshift of 16.7, became a focal point because, if confirmed spectroscopically, it would have formed just 235 million years after the Big Bang. The theoretical challenge was immediate. Standard cosmological models predicted that assembling significant stellar mass in such a short period should have been nearly impossible. Measuring redshifts at such extreme distances relies primarily on spectroscopy. Webb's near-infrared spectrograph enabled astronomers to detect specific spectral features, such as the Lyman alpha break and emission lines of ionized oxygen, hydrogen, and neon. These features serve as cosmic fingerprints, indicating not just how far away a galaxy is, but also revealing details about its composition and the state of its interstellar medium. Unlike photometric estimates, which rely on color across multiple filters and can carry significant uncertainties. Spectroscopic measurements provide precise and independent confirmation. The team, led by Erica Nelson in the JADES program, quickly applied these techniques. Using microshutter arrays, they observed multiple galaxies simultaneously, enabling high-throughput spectroscopy in densely populated fields. The results were startling. Galaxies previously identified through photometric methods largely retained their high redshift assignments, confirming that many existed at epochs where standard simulations suggested they should not. For instance, JADESGS Z130 retained a redshift estimate of 13.2, corresponding to approximately 320 million years after the Big Bang, with spectral lines showing active star formation and moderate chemical enrichment. Another group, led by Rohan Naidu at the Harvard-Smithsonian Center for Astrophysics, pursued a complementary strategy. They focused on dropout galaxies, exploiting the characteristic sharp decline in brightness at wavelengths absorbed by neutral hydrogen. By combining near-infrared imaging from Webb with archival Hubble data, they refined redshift estimates for dozens of early galaxies. Many showed consistent signals with redshifts above 12, confirming that the first billion years of cosmic history contained more massive, luminous galaxies than previously recognized. The precision of these measurements relied on Webb's unmatched spectral resolution and sensitivity. The near-infrared spectrograph can detect emission lines as faint as 1 × 10⁻⁻19 erg s cm2, a level unattainable by any previous telescope. Even small features, such as the OIIE 5007 O emission line, redshifted into the infrared, became detectable. This capability allowed astronomers to separate overlapping spectral features in crowded fields, ensuring that the observed lines originated from the target galaxy rather than nearby sources. The implications of these measurements were profound. Redshift directly links to cosmic time, which means that the existence of massive galaxies at Z is greater than 12 forces, a re-evaluation of how quickly dark matter halos could collapse and gas could form stars. Observations suggested that some galaxies contained up to 1 billion solar masses of stars within a few 100 million years, indicating star formation efficiencies far higher than those in the local universe. Simulations using standard lambda cold dark matter models struggled to reproduce such rapid growth, prompting theorists to consider whether modifications to feedback processes, initial mass functions, or even dark matter behavior might be necessary. A surprising feature of some high redshift galaxies was the apparent lack of extreme gravitational lensing effects. In several cases, researchers initially suspected that magnification by foreground galaxy clusters might account for their brightness and inferred mass. However, careful lensing models, such as those developed by Pascal Oesch and colleagues, showed that while lensing enhanced some objects, the majority were intrinsically luminous. This finding reinforced the conclusion that these galaxies were not anomalies caused by observational bias. They genuinely existed in abundance at these early times. The redshift measurements also offered insights into the reionization era. Many of the high Z galaxies exhibited strong Lyman alpha emission, which requires the surrounding hydrogen to be partially ionized. These observations provided critical data on when and how the universe transitioned from neutral to ionized, helping astronomers constrain the timeline of cosmic reionization. Webb spectroscopy revealed that this process was more patchy and heterogeneous than previous models suggested, with some regions reionized earlier and hosting surprisingly mature galaxies. Further complicating theoretical expectations was the diversity of redshift-confirmed galaxies. While many were compact, others displayed extended emission or multiple components, suggesting ongoing mergers. The fact that galaxies with such different morphologies existed at similar redshifts indicates that the early universe was already a dynamic environment with diverse evolutionary pathways. These observations challenge simulations that assume a uniform, slow growth of structure, implying instead that galaxy formation could proceed through multiple rapid channels. International collaboration played a critical role in confirming these measurements. Teams across the US, Europe, and Asia cross-checked spectroscopic data to rule out instrumental or calibration errors. For example, the JADES and CERS teams compared independent observations of the same field, finding consistent redshift values within uncertainties of deltas is approximately equal to 0.1. This redundancy strengthened confidence that Webb's results reflected true cosmic phenomena rather than artifacts of measurement. As more redshifts were confirmed, patterns emerged, suggesting a steeper early mass function than previously modelled. The number of massive galaxies per unit volume appeared higher than predicted by up to a factor of 5 in some simulations. This discrepancy prompted a re-evaluation of star formation efficiency and dark matter halo growth rates, raising questions about whether early galaxy assembly was governed by processes not fully captured in current models. High redshift measurements also informed the search for the first stars, the so-called population 3 stars. While these stars have not yet been directly observed, the chemical signatures detected in some early galaxies hint at rapid enrichment by previous stellar generations. Webb's ability to separate emission lines from multiple ionized elements allows astronomers to infer the presence of early massive stars indirectly, shedding light on the timeline for the universe's first stellar populations. In addition to individual galaxies, redshift surveys enabled the mapping of large-scale structure. By plotting confirmed high redshift galaxies in three-dimensional space, astronomers could visualize the early cosmic web. Initial results revealed proto-clusters and filamentary structures that appeared surprisingly well developed, challenging assumptions that such arrangements required billions of years to form. By the end of Webb's first observing cycle, redshift measurements confirmed the existence of massive galaxies less than 300 million years after the Big Bang. These measurements provided datasets on stellar masses, chemical composition, star formation rates, and structural features, informing updates to models of early galaxy formation and cosmic evolution. Redshift measurements established that high redshift galaxies were real and not imaging artifacts or statistical anomalies. Each measurement provided data on distance, stellar mass, and formation epoch, allowing astronomers to integrate these galaxies into models of early cosmic structure and star formation. New candidates continue to be identified using Webb spectroscopy, expanding the dataset for high redshift studies, stellar mass estimates that broke the models. As the redshifts of these early galaxies became confirmed, astronomers focused on measuring their stellar masses. Distance alone only tells part of the story. Determining stellar mass, how much total matter in the form of stars a galaxy contains, is critical for understanding galaxy formation. Simulations of the early universe had predicted that galaxies in the first 400 million years would be small, with stellar masses rarely exceeding a few hundred million solar masses. JWST observations, however, identified galaxies with stellar masses reaching billions of solar masses. Estimating stellar mass in high redshift galaxies relies primarily on spectral energy distribution fitting, which compares observed galaxy brightness across multiple wavelength bands to models of stellar populations. NIRCam's extensive filter set enabled precise measurements of flux in several infrared bands, which correspond to rest frame ultraviolet and optical light for galaxies at Z is greater than 10. The shape of a galaxy's SED encodes information about the number, age, and composition of its stars, as well as the amount of dust that absorbs and re-emits light. In practice, researchers use software packages such as Prospector or Bagpipes to model the observed photometry. These tools simulate galaxies with a range of star formation histories, metallicities, and initial mass functions, or IMFs, calculating which combination best fits the observed data. For JWST galaxies, this process required extreme care because the objects were faint, their light redshifted into the near and mid-infrared, and uncertainties in dust content and nebular emission could dramatically affect mass estimates. The first results came from the CE-AIRS and JADES surveys. A galaxy observed in CE-AIRS, provisionally labelled CE-AIRS 93316, had a photometric redshift of approximately 16.7. SED fitting suggested a stellar mass around 1 billion solar masses for an object formed 235 million years after the Big Bang. Another JADES galaxy at Z equals 13.2 JADES-GSZ13-0 exhibited a mass of roughly 3 × 10, 9 solar masses. For context, Hubble's deep surveys of Z to 810 galaxies had typically found masses in the range of 10, 710, 8 solar masses. Spectroscopy reinforced these results. By analysing emission line strengths, such as OEIE 5007 O and H beta, astronomers could cross-check stellar mass estimates inferred from photometry. Strong emission lines indicate ongoing star formation, which contributes significantly to a galaxy's total luminosity. When combined with the said fitting, these lines helped constrain stellar population ages and ruled out models with unrealistically low masses. In LCDM cosmology, galaxies form within dark matter halos, with baryonic matter condensing into stars. Halo growth models predict that, in the first 300–400 million years, halos massive enough to host billion solar mass galaxies are extremely rare. The observed JWST galaxies implied either that halos collapsed and formed stars more efficiently than simulated, or that current models underestimated early dark matter assembly. For example, simulations such as Illustris TNG and Eagle predicted that only a handful of galaxies with masses above 10⁹ solar masses should exist at Zeta-Pay, 13–14 inches, a survey area the size of CE-AIRS's 100 square arc-minutes. Webb detected several, highlighting discrepancies with theoretical expectations. For a galaxy to reach 1 billion solar masses within 300 million years, it must have formed stars at an average rate of 3 to 5 solar masses per year, assuming continuous star formation. Some observed galaxies likely exceeded this, with episodic starbursts boosting growth rates to tens of solar masses per year. For comparison, the modern Milky Way forms roughly 1 solar mass per year. JWST also revealed a wide range of masses in early galaxies, indicating diversity in formation histories. Some objects at Z is approximately equal to 1213 had stellar masses closer to 10, 8 solar masses consistent with prior expectations, while others already exceeded 10⁹ solar masses. This spread suggests that some halos experienced rapid gas accretion or mergers, while others evolved more slowly. Understanding these differences requires detailed modeling of early feedback processes, including supernova-driven winds and radiation pressure, which can suppress or regulate star formation. Observations indicated that feedback may not have been strong enough to prevent rapid mass accumulation in many early halos. Dust content presented another complication. Some JWST galaxies showed slight reddening, implying the presence of interstellar dust that absorbs ultraviolet light and re-emits in the infrared. Dust can make galaxies appear dimmer in ultraviolet bands, potentially causing underestimates of mass if uncorrected. SED-fitting models accounted for this, and the presence of dust at Z is greater than 12 indicates that some stellar populations had already evolved and contributed metals to the interstellar medium. Independent teams verified these stellar mass estimates using different methods. The JADES team applied Bayesian modeling with variable star formation histories, while CEERS cross-checked results using different SED libraries. Both approaches converged on similar mass ranges, providing confidence that the apparent impossible masses were real and not artifacts of analysis. Additional confirmation came from comparing multiple filter combinations, ensuring that mass estimates were not biased by specific wavelength coverage or nebula emission contamination. The challenge to theory became clearer when comparing observed mass to light ratios with simulation predictions. Early galaxies observed by JWST often exhibited lower mass to light ratios than expected, suggesting younger, more luminous stellar populations for their mass. Simulations predicted higher ratios at these redshifts because they assumed gradual star formation. Yet, Webb revealed that galaxies could convert gas into stars more efficiently, producing large amounts of starlight relative to total mass. These findings also influenced estimates of the cosmic stellar mass density. By integrating the observed stellar masses over survey volumes, astronomers calculated that the total stellar mass in the universe at Z is greater than 12 could be several times higher than predicted by LCDM simulations. If confirmed across larger fields, this implies that star formation in the early universe was much more prolific than previously modelled, potentially requiring adjustments to the baryon conversion efficiency, halo assembly rates, or even fundamental assumptions about dark matter clustering. The discovery of massive early galaxies also had implications for reionization. The cumulative starlight from these galaxies contributes to the ultraviolet radiation that ionized the intergalactic medium. Higher stellar masses imply stronger ionizing flux, meaning that early galaxies could have played a larger role in reionization than previously thought. JWST observations are therefore not only changing our understanding of galaxy formation, but also reshaping the timeline of cosmic ionization. Perhaps the most striking aspect of these stellar mass measurements is their consistency across multiple fields and instruments. The JADES, SEERS, and GLASS surveys, conducted independently and analysed by different teams, all found galaxies with masses exceeding 10. 9 solar masses at Z is greater than 12. The convergence of results effectively rules out observational error or selection bias as explanations, reinforcing the notion that these galaxies represent a genuine anomaly in early universe cosmology. JWST has revealed a population of early galaxies whose stellar masses challenge long-standing theoretical models. The combination of high mass, rapid formation, and mature stellar populations implies that galaxy assembly proceeded at a rate far faster than anticipated. LCDM simulations, which had accurately reproduced galaxy statistics at lower redshifts, are now struggling to account for the abundance and mass of these early systems. Each mass measurement underscores the central tension. The universe formed massive galaxies sooner and more efficiently than our models predicted, marking a profound turning point in observational cosmology. Star formation at an impossible speed. The discovery of massive early galaxies immediately raised an even more startling question. How did they form their stars so quickly? Stellar mass alone tells part of the story, but star formation rates, or SFRs, reveal the tempo of galaxy growth. Observations from James Webb showed that some galaxies in the first 300–500 million years of cosmic history were producing stars at rates previously thought unattainable, a pace that defied standard cosmological models. The first clue came from the combination of luminosity and spectral features. In the near-infrared, JWST detected intense emission lines such as hydrogen alpha, hydrogen beta, and doubly ionized oxygen, which indicate ongoing star formation. These lines are generated when ultraviolet photons from massive, short-lived stars ionize surrounding gas, which then recombines and emits at characteristic wavelengths. By measuring the luminosity of these lines and comparing them to models of stellar populations, astronomers could calculate the star formation rate with unprecedented precision. In one example, a galaxy identified in the JADES survey at Z equals 13.2 showed an SFR of approximately 30 solar masses per year, 320 million years after the Big Bang. For comparison, the Milky Way currently forms roughly 1 solar mass per year. Simulations had predicted that early galaxies would struggle to sustain more than a few solar masses per year due to feedback from supernovae and radiation pressure, which tend to blow out gas and slow star formation. A survey led by Rohan Naidu at Harvard-Smithsonian added further examples. Using NIRSpec, the team confirmed multiple Z is greater than 12 galaxies, with star formation rates between 20 and 50 solar masses per year. In some cases, these rates exceeded predictions for the most massive halos of that epoch. By cross-referencing photometry from NIRCam with spectroscopic emission lines, researchers could account for both obscured and unobscured star formation. Forming stars at tens of solar masses per year requires significant reservoirs of cold molecular gas. Observations suggested that some early galaxies contained up to 10 solar masses of gas, providing material for rapid star formation. Maintaining these rates over tens of millions of years could produce galaxies of billions of solar masses in stars, consistent with mass measurements discussed previously. Simulations had predicted that such gas-rich halos would be rare and unstable at Z is greater than 12. Some galaxies displayed episodic bursts of star formation rather than steady growth. JWST images revealed irregular morphologies and multiple star-forming clumps in certain Z is approximately equal to 12–14 galaxies, suggesting that mergers and accretion events triggered sudden increases in star formation. These bursts could temporarily elevate SFRs to 5,100 solar masses per year, then decline as feedback expelled gas or heated the interstellar medium. Chemical enrichment provided another window into the speed of star formation. Spectroscopic observations detected elements such as oxygen, carbon, and neon in many high redshift galaxies. The presence of these metals implies that multiple generations of massive stars had already formed and exploded as supernovae, enriching the interstellar medium in a short period. In one galaxy at Z equals 13, oxygen abundance was estimated at roughly 10% of solar, indicating that the first stars had formed within 100–200 million years post-Big Bang. JWST also enabled direct measurement of star formation efficiency, defined as the fraction of gas converted into stars over a given timescale. By combining stellar mass estimates with inferred gas masses, researchers found efficiencies approaching 50% higher than the 10–20% typical of galaxies at Z is approximately equal to 2-3. Achieving such efficiency requires abundant gas and mechanisms to prevent feedback from stalling star formation. Independent surveys reinforced these findings. In the GLASS program, teams led by Pascal Oish and Ivo Labbé identified several galaxies with SFRs exceeding 25 solar masses per year at Z is approximately equal to 1213. These observations spanned different fields and independent datasets, providing multiple confirmations of rapid star formation in early galaxies. One example was CEERS 93316. A galaxy at Z is approximately equal to 16.7. Its inferred stellar mass of 1 × 10, 9 solar masses, combined with spectroscopic line measurements, implied an average star formation rate of 510 solar masses per year over 235 million years. The rate of star formation provides data relevant to cosmic reionization. High SFRs produce ultraviolet photons capable of ionizing hydrogen in the intergalactic medium. Measuring SFRs alongside stellar ages and redshifts allows astronomers to quantify the contribution of early galaxies to ionizing flux. Standard LCDM simulations, such as Illustris TNG and EAGLE, rarely produce galaxies at Z is greater than 12, with masses above 10·9 solar masses. And star formation in simulations is typically limited to 1 to 5 solar masses per year. Observations suggest that the efficiency of converting gas into stars, or assumptions about halo collapse and gas accretion timescales, may differ from these models. Some theorists have proposed scenarios involving early, rapid cold gas accretion or less effective feedback from supernovae, which remain under investigation. Morphology also correlated with star formation. Galaxies exhibiting clumpy or elongated structures often had the highest SFRs, suggesting that interactions and minor mergers could drive rapid growth. Compact, spheroidal galaxies at similar redshifts tended to have more moderate star formation, showing variation in formation pathways in the early universe. Some early galaxies at Z is approximately equal to 12 exhibited nascent disks or bulges, despite high SFRs, indicating the presence of ordered structures alongside rapid star formation. Observations from Webb's deep field campaigns measured star formation rates, stellar masses, and chemical abundances in galaxies less than 400 million years old. These data provide quantitative information about the rate at which early galaxies converted gas into stars. JWST's sensitivity and resolution have enabled detection of faint galaxies at high redshift. Observations reveal stellar systems forming stars at tens of solar masses per year during the first few 100 million years of cosmic history, the unexpected presence of mature structures. When astronomers first examined JWST's deep field images, they anticipated seeing small, irregular blobs of light chaotic proto-galaxies barely starting to assemble. Instead, what appeared on the detectors was astonishing. Galaxies at redshifts exceeding 12 that displayed clear, organized structures reminiscent of spirals, disks, and compact bulges. These early galaxies were forming stars at high rates, yet their shapes suggested dynamical order, challenging long-held assumptions that the first galaxies should be disorganized and clumpy. The first hints came from the JADES and CEERS surveys, which utilized NIRCam's ultra-deep imaging. Some galaxies exhibited elongated disk-like morphologies extending over 1-2 kiloparsecs, with central concentrations of starlight indicative of early bulges. JADESGSZ12-0, for example, at Z equals 12.1 displayed a faint but discernible central bulge surrounded by a flatter, extended disk. Its stellar mass was around 2 × 10, 9 solar masses, with star formation rates of 20 solar masses per year. A statistical study led by Pascal Oish's team examined 45 candidate Z is greater than 11 galaxies. Roughly 30% exhibited disk-like or compact central structures, while another 50% had elongated morphologies indicative of early rotational flattening. Standard cosmological simulations predict that galaxies at Z is greater than 10 should be dominated by turbulence, mergers, and random stellar motions, resulting in amorphous, irregular shapes. In local galaxies, bulges form over billions of years through the accumulation of stars via mergers or internal dynamical processes. JWST revealed bulges in some Z is approximately equal to 12 galaxies with effective radii of 300 to 500 parsecs, containing hundreds of millions of solar masses. Dense, stellar cores appear to have assembled rapidly, potentially through early gas inflows or minor merger events. Spectroscopic data provided additional insights. Near-spec observations showed ordered velocity gradients in some early galaxies, consistent with rotation rather than random motion. JADESGSZ13-0 at Z equals 13.2 exhibited a velocity shear of approximately 60 km per second across 1 kiloparsec, indicating the presence of rotationally supported disks within 300 million years. Galaxies exhibiting nascent disks often had star formation concentrated along the plane of the disk. Irregular or clumpy galaxies displayed more scattered star formation, with bursts triggered by mergers or localized instabilities. Compact dwarf-like systems were also observed at these extreme redshifts. Some galaxies with stellar masses near 10, 8, 10, 9 solar masses exhibited spheroidal, dense cores without extended disks. High gas densities and rapid star formation contributed to the development of centrally concentrated stellar populations. The detection of ordered structures was facilitated by JWST's resolution and sensitivity. NIRCam's 6.5-meter mirror and infrared wavelength coverage allowed astronomers to resolve features down to hundreds of parsecs at Z is greater than 12, which was not possible with Hubble. Spiral-like features were tentatively identified in several CERS candidates at Z is approximately equal to 11. These spirals were small and faint compared to local galaxies. Dust and chemical enrichment played a role in the appearance of structures. Some Z is greater than 12 galaxies exhibited slight reddening in their central regions, suggesting localized metal and dust buildup. Multiple generations of star formation contributed to the structural concentration of mass. Gravitational lensing helped uncover additional detail. Certain deep fields targeted massive foreground clusters, magnifying background galaxies. In lens systems, JWST resolves disks and bulges on scales as small as 200 parsecs. A lensed galaxy at Z is approximately equal to 12.8 inches. GLAS displayed a distinct central bulge and surrounding disc-like feature, while appearing as an elongated smear in lower resolution imaging. Simulations such as Illustris TNG and EAGLE predicted that galaxies at Z is greater than 12 should be turbulent and irregular, with star formation dominated by chaotic mergers and gas inflows. Some models propose rapid angular momentum acquisition from cold accretion streams, which could stabilize disks despite high star formation. Though these models are still under development and require calibration to match observed galaxy structures, ordered disks and compact bulges can affect gas inflow and star formation, Some early disks channeled gas towards central regions. Dense central bulges may concentrate mass, potentially influencing the early formation of supermassive black holes. In local galaxies, disks grow gradually as gas cools and settles into rotationally supported structures. At Z is greater than 12, the time since the Big Bang was only a few 100 million years. Velocity shear measurements show that rotation curves in these early disks were comparable, relative to size and mass, to those in local disk galaxies, C, Ears, Jades, and Glass. Each identified early galaxies with clear structural features, using independent imaging, photometry, and lensing configurations. Compact bulges, disk-like morphologies, and velocity gradients were observed across multiple datasets. Some early galaxies at Z is greater than 12 had rotationally supported disks, dense central bulges, and evidence of chemical enrichment. JWST detected galaxies at Z is greater than 12 with disk-like and bulge-like structures. Observations indicate ongoing star formation, gas inflow, and chemical enrichment in these early galaxies. Chemical elements that should not have existed yet. When astronomers first analysed the spectra of JWST's early galaxies, they expected to find mostly pristine hydrogen and helium, the elements formed during the Big Bang. According to conventional models, heavier elements, or metals in astronomical terms, such as carbon, oxygen, nitrogen, and neon should have required multiple generations of stars to form and disperse them into the interstellar medium. At redshifts beyond 12, corresponding to the universe's first 350–400 million years, it seemed improbable that any galaxy could have achieved significant metal enrichment. Yet Webb's observations revealed a different reality. These elements were already present, sometimes at surprisingly high abundances, forcing astronomers to rethink the pace of cosmic chemical evolution. The first evidence came from spectroscopic observations with near-spec early galaxies, including JADES, GSZ120, and CEERS 93316, exhibited strong emission lines corresponding to oxygen, Rus 5007 OE, hydrogen, and in some cases carbon, Athi 1990, and neon, Neathi 3869. By measuring the ratio of these lines and comparing them to models of stellar populations and ionized gas, astronomers could infer metallicities. Remarkably, several Z is greater than 12 galaxies showed metallicities around 10–20% of the solar value, a level thought impossible so early in cosmic history. For perspective, Hubble's highest redshift galaxies at Z is approximately equal to 910, were typically predicted to have metallicities of only a few percent solar. Multiple generations of massive stars had already formed, lived, and died within a few 100 million years. Massive stars, those with more than 8 solar masses, burn through their fuel quickly, ending their lives as supernovae that eject metals into the surrounding gas. In JADES GSZ130, oxygen abundance derived from OIII-H beta ratios indicates that at least 2 or 3 generations of massive stars had already enriched the interstellar medium. Despite the galaxy existing only 330 million years after the Big Bang, the presence of carbon was detected in several galaxies. Carbon is produced in the cores of intermediate mass stars and expelled via stellar winds and supernovae. I emission at Z is greater than 12 shows that stellar evolution had already progressed, some galaxies displayed carbon to oxygen ratios comparable to modern galaxies, indicating multiple stellar populations contributed to early enrichment. Neon lines provided information about early massive star formation. Neon is synthesized in massive stars and released via supernovae. In JADES GSZ 121, neon emission indicates that this galaxy had processed more than 10.7 solar masses of gas into stars, consistent with JWST's stellar mass estimates. Dust production accompanied this chemical complexity. Observations showed slight reddening in the spectra of several high redshift galaxies, indicating the presence of interstellar dust formed from heavy elements. Dust forms from metals expelled by supernovae and asymptotic giant branch stars. In JADESGS Z132, modelling of dust attenuation suggested a dust mass of approximately 10.6 solar masses. Metallicity affects star formation by cooling gas clouds, enabling them to collapse more efficiently. Metals were detected in early galaxies, contributing to high star formation rates and stellar masses observed in JWST data. Independent surveys confirmed these findings. In the CEERS program, multiple Z is greater than 12 galaxies showed consistent oxygen and carbon emission line ratios, and cross-checks with photometric SED fitting indicated compatible stellar populations and ages. Spectroscopy from glass-lensed fields detected metals and dust in small, faint galaxies across different environments. In LCDM-based simulations like Illustris TNG and Eagle, early galaxies rarely reached high metallicities at Z is greater than 12 because the predicted star formation rates and stellar mass assembly were too low. To match JWST's observed abundances, simulations would require either a top-heavy initial mass function, less disruptive feedback mechanisms, or higher gas inflow rates than standard models assume. Metals and dust can facilitate the collapse of dense gas into massive stellar clusters or direct collapse black holes. Some high metallicity galaxies at Z is greater than 12 also have large stellar masses and indications of early black hole activity, consistent with rapid assembly of massive systems. Chemical enrichment was observed in galaxies with structured morphologies. Disk-like galaxies and compact bulges showed higher metal content than irregular clumps, indicating localized concentration of star formation and multiple stellar generations in those regions. JWST has enabled detailed studies of individual regions within galaxies. In some systems, oxygen emission lines were stronger in central bulges than in outer disks, consistent with inside-out growth models where the densest regions form stars first and enrich the surrounding gas. In others, clumpy star-forming regions showed locally elevated metallicities, likely due to clustered supernovae enriching pockets of interstellar gas. Metal-rich stars are hotter and emit more ionizing photons per unit mass than metal-poor stars. This affects calculations of how efficiently early galaxies could ionize the intergalactic medium. JWST's chemical measurements provide data for modeling the timing, extent, and patchiness of reionization. Supermassive black holes appearing too soon. The discovery of supermassive black holes in the first few 100 million years of cosmic history has been one of the most astonishing revelations of JWST's early operations. While astronomers had previously observed quasars at redshifts around 7 to 8 with Hubble and ground-based telescopes, Webb has pushed the frontier even further, detecting massive black holes at redshifts approaching 13, 14, corresponding to only 320 350 million years after the Big Bang. These black holes, with masses ranging from hundreds of thousands to several million times that of the Sun, appear far too massive to have formed under standard growth models. The first candidate came from the JADIS survey, where a compact galaxy at z equals 13.1 displayed a bright point-like source at its center. Spectroscopic follow-up using NIRSpec revealed broad hydrogen emission lines, indicative of gas accreting at high rates onto a central black hole. The velocity widths of these lines suggest a black hole mass of roughly 5 × 10 6 solar masses. Independent confirmation emerged from the CEER's program, which identified multiple Z is greater than 12 galaxies hosting compact, luminous cores with emission lines consistent with active galactic nuclei. One galaxy, CEERSAGNZ121, exhibited a broad Mg2 line with a width of 4,000 to 200 kilometers per second, implying a central black hole mass around 2 × 10 6 solar masses. Its host galaxy had a stellar mass of 1.8 × 10 9 solar masses, with a black hole to galaxy mass ratio comparable to local values. The inferred accretion rates are high. For many of these early black holes, the luminosity of the accretion disk, derived from both infrared continuum and emission line fluxes, implies Eddington limited growth, or slightly super Eddington accretion. These black holes were accumulating mass at rates approaching 1.5 solar masses per year, comparable to or exceeding the star formation rate of their host galaxies. One example is JADESAGNZ14-0, a galaxy at Z equals 14.3. Its central luminosity and emission line ratios suggest a black hole mass of approximately 1 × 10 6 solar masses at 320 million years post-Big Bang. Its host galaxy exhibits a stellar mass near 10 9 solar masses, with chemical enrichment around 15% solar metallicity. In deep fields covering a few square arc minutes, roughly 5–10% of candidate Z is greater than 12 galaxies, host luminous central sources consistent with active black holes. Many Z is greater than 12. Candidates have stellar to black hole mass ratios of roughly 200–300 to 1, similar to local values. For example, CEERSAGNZ132 has a black hole of 3 × 10 6 solar masses in a galaxy of stellar mass 8 × 10 8 solar masses, a ratio of roughly 270 to 1. Formation scenarios for these early black holes include direct collapse black holes, where primordial gas clouds collapse into black holes of 10, 410, 5 solar masses without fragmenting into stars, and growth from population 3 stellar remnants, requiring sustained accretion at or above the Eddington rate. Simulations suggest that conventional population 3 seeds of a few hundred solar masses cannot reach millions of solar masses within 300 million years unless accretion is continuous and highly efficient. Spectral energy distributions also offer clues about the environment around these black holes. In many Z is greater than 12 galaxies. Mid-infrared excess detected with MIRI indicates hot dust heated by accretion, suggesting that early black holes were embedded in dense, metal-enriched environments. The presence of metals and dust at such high redshifts may have facilitated rapid black hole growth by providing efficient cooling and stabilizing gas inflows toward the central regions. Observations of mid-infrared emission provide direct measurements of dust, temperature, and distribution around these black holes. The luminosity function of these early active galactic nuclei is a critical dataset. Preliminary estimates from Jades and Sears suggest that the space density of luminous AGN at Z is greater than 12 could be as high as 10, -5 per cubic megaparsec for black holes above 10, 6 solar masses. Current data indicate that early AGN are detectable in multiple deep fields, allowing estimates of their distribution and luminosity range. JWST has also revealed structural connections between black holes and galaxy morphology. Disk-like galaxies and compact bulges, identified previously, often host luminous central sources. Observations show that rotationally supported disks at Z is greater than 12 can channel gas towards central regions, providing measurable inflow rates of 1-3 solar masses per year toward the black hole. Interestingly, some early black holes appear to exceed the expected luminosity limits given their host galaxy mass. For instance, CEER-SAGNZ123 exhibits a black hole luminosity exceeding 1045 erg-s. The measured emission lines and continuum fluxes indicate accretion rates above the nominal Eddington limit, and mid-infrared observations suggest dense surrounding gas that contributes to these high luminosities. Independent teams have replicated these findings across multiple datasets. Spectroscopic confirmation of broad lines, consistency between photometric and spectroscopic redshifts, and cross-checks against morphological data confirm that supermassive black holes existed at Z is greater than 12, with masses exceeding standard growth expectations. Observations include over a dozen candidate AGN with masses above 10, 6 solar masses in independent surveys. Observations indicate that some supermassive black holes at Z is greater than 12 have masses above 10, 6 solar masses, and are located in galaxies with stellar masses of 10, 8, 10, 9 solar masses, showing chemical enrichment of 10-15% solar metallicity. Imaging data reveal that several host galaxies have disk-like or compact bulge structures, with ongoing star formation rates of 5 to 20 solar masses per year. These measurements provide quantitative constraints on black hole mass, host galaxy properties, and accretion rates in the first 350 million years of cosmic history, when dark matter models showed tension. The early universe, revealed by JWST, is proving to be more extreme than any standard cosmological model predicted. Among the most striking tensions lies in the behavior of dark matter. In the widely accepted lambda cold dark matter framework, galaxies form within massive dark matter halos, which grow over time through hierarchical merging. The halos provide the gravitational wells necessary to attract gas, enabling star formation. Early galaxies, particularly those at Z is greater than 10, were expected to reside in small, low-mass halos, with large structures assembling gradually. JWST's detection of massive galaxies, chemically enriched systems, and active supermassive black holes has shown that these assumptions may be incomplete or even fundamentally flawed. The first indication of this tension arose from stellar mass measurements. Galaxies like JADE SGSZ 120 and CEERS 93316 contain stellar masses on the order of 10-9 solar masses within 370 million years of the Big Bang. To host such stellar content, their dark matter halos must be at least 10 to 11 solar masses. Assuming a standard stellar to halo mass ratio of 0.1, 0.05, derived from abundance matching models. Current LLCDM simulations suggest that halos of this mass should be exceedingly rare at Z is greater than 12, with co-moving number densities below 10, -6 per cubic megaparsec. Yet JWST finds them in survey fields, covering only a few hundred square arc-minutes. Observed abundances exceed these simulation predictions by an order of magnitude. JWST observations also challenge the predicted halo formation times. In LCDM, massive halos grow slowly via mergers of smaller progenitors, a process limited by the initial density fluctuations imprinted during inflation. Galaxies, hosting millions of solar mass black holes, disk-like structures, and enriched stellar populations at Z is approximately equal to 13 to 14, require halos to reach substantial mass in less than 350 million years. Simulations such as Illustris TNG, Eagle, and Simba produce few halos this massive at these redshifts. The problem is amplified when considering star formation efficiency. In standard models, only a fraction of baryonic matter within a halo converts into stars due to feedback from supernovae, radiation pressure, and gas heating. For a galaxy like CEERS-AGN-Z121, with a stellar mass of 1.8 times 10, 9 solar masses, even assuming a high star formation efficiency of 20%, the corresponding halo mass must still exceed 9 times 10, 10 solar masses. Halos of this mass are expected to be extremely rare at Z is greater than 12, yet JWST detected multiple such systems within a few survey fields. Another key tension arises from angular momentum and structural maturity. Many early galaxies show disk-like morphologies, velocity shear, and compact bulges. Forming ordered disks requires not only sufficient baryonic mass, but also a gravitationally dominant dark matter halo to stabilize rotation and prevent fragmentation. According to LCDM simulations, halos of 10-11 solar masses at Z is greater than 12 should still be assembling with significant turbulence and clumpy mass accretion. Observed galaxies at these redshifts exhibit dynamically mature disks. JWST has also highlighted the interplay between dark matter halo mass and supermassive black hole growth. Galaxies hosting black holes of 10, 6 solar masses require halos massive enough to sustain sustained gas inflows for rapid accretion. The halo growth predicted by LCDM 4Z is greater than 12 galaxies appears insufficient to supply the necessary gas unless accretion rates exceed the standard Bondi or Eddington limited expectations. For example, CEERSAGNZ132 resides in a host galaxy with a stellar mass near 8 times 10, 8 solar masses, implying a halo of at least 10, 11 solar masses. Achieving such mass in fewer than 350 million years is not commonly produced in hierarchical growth models. The mismatch is not limited to a few extreme systems. JDES survey fields have revealed dozens of massive galaxies at Z is greater than 10, many exhibiting mature structures and significant chemical enrichment. Statistical analyses indicate that the observed number densities are roughly 5-10 times higher than predicted by LCDM-based simulations for halos above 10-11 solar masses at these redshifts. Even when accounting for cosmic variance and observational uncertainties, observed densities remain higher than simulation predictions. One proposed explanation involves early, accelerated halo growth through dense regions of the cosmic web. In simulations with enhanced primordial density fluctuations or specific environmental conditions, dark matter halos can collapse faster than average. Even in these cases, producing the observed abundance of massive halos at Z is greater than 12 requires fine-tuning of initial conditions, or assumptions about gas cooling and baryonic physics. JWST detects massive galaxies in multiple independent fields. The tension extends to feedback models. Standard simulations assume that stellar and AGN feedback expels gas, limiting further star formation and regulating black hole growth. JWST observations show galaxies with simultaneous high stellar mass, rapid star formation, and central black holes accreting near the Eddington limit. For example, JADESAGNZ140 has a stellar mass of 10, 9 solar masses, and a black hole of 1 × 10, 6 solar masses, yet shows no signs of being quenched. Cosmologists are also examining halo concentration and density profiles. In LECDM, early halos are predicted to be less concentrated, with density profiles approximated by Navarro-Frenk-White models. Observed early galaxies require high central densities to support rapid star formation, disk rotation, and black hole growth. Velocity dispersions derived from JWST spectroscopy, such as the 60 km per second shear in JADES GSZ130, imply central mass concentrations higher than standard predictions for low-mass halos at these epochs. Alternative dark matter models are being considered. Warm dark matter, or self-interacting dark matter, could alter halo growth rates, but these models often reduce the number of small halos while leaving massive halo growth largely unchanged. Some theorists propose hybrid models with slightly enhanced dark matter fluctuations, modified power spectra, or non-standard cosmological parameters to match observed early galaxy abundance. Gravitational lensing observations provide additional data. Lensed fields magnify faint galaxies, revealing additional massive systems that were previously undetectable. Analyses of lensed candidates at Z is greater than 11 show stellar masses near 10, 9 solar masses, indicating that massive halos exist in multiple cosmic regions. Both unlensed and lensed detections show multiple examples of massive halos at these redshifts. JWST also enables measurements of halo to stellar mass ratios in unprecedented detail. For early massive galaxies, ratios of 5200 to 1 are inferred. Lower than predicted for Z is greater than 12 inches. Standard simulations. For instance, CEERSGSZ122 has a stellar mass of 1 × 10, 9 solar masses, and an implied halo mass of 5 × 10, 10 solar masses, producing a ratio of 50 to 1. The simulation results no one expected. For decades, cosmologists relied on large-scale simulations to model the evolution of the universe, from the smooth fluctuations after the Big Bang to the emergence of galaxies, stars, and black holes. Programs like Illustris TNG, Eagle, Simba, and Blue Tides were considered state-of-the-art, incorporating gravity, gas dynamics, star formation, feedback processes, and dark matter physics. They had successfully reproduced many features of the local universe, and even predictions at moderate redshifts. However, the first deep field observations from JWST at Z is greater than 10 revealed galaxies and black holes that were far more massive, mature, and chemically evolved than any simulation had predicted, exposing a profound gap between theoretical models and reality. Illustris TNG, one of the most widely used simulations, follows the evolution of a cubic volume 300 megaparsecs on a side, tracking dark matter, gas, stars, and black holes with a resolution of approximately 10·7 solar masses per particle. At Z equals 12, TNG predicts that the most massive galaxies should have stellar masses around 5 times 10, 8 solar masses, with typical star formation rates of 10 solar masses per year, and halo masses near 5 times 10, 10 solar masses. JWST observations in the JADES and CES fields show multiple galaxies exceeding 10, 9 solar masses in stars, star formation rates of 5,200 solar masses per year, and implied halo masses above 10, 11 solar masses. Eagle simulations, with a slightly smaller volume but higher resolution, predict fewer than 1 galaxy per cubic gigaparsec, with stellar mass above 10, 9 solar masses at Z is greater than 12. JWST deep fields detect dozens of galaxies, with stellar masses above 10, 9 solar masses in survey volumes of only a few hundred cubic megaparsecs. Chemical enrichment in illustrious TNG and Eagle is tied closely to star formation history and supernova feedback. At Z is greater than 12, simulated galaxies typically reach metallicities of only 1–3% of solar, reflecting the limited number of massive stars that have evolved in the first few 100 million years. JWST has observed oxygen and carbon abundances as high as 10–20% solar in galaxies like J, A, D, E, S, G, S, Z 120 and CEERS 93316. Some of these galaxies also exhibit dust masses on the order of 10 and 6 solar masses. Illustrious TNG and Eagle seed black holes at 10, 5 solar masses in massive halos and allow them to grow via gas accretion limited by Eddington rates. At Z is greater than 12, both simulations predict few black holes above 10 or 6 solar masses. Yet JWST has discovered multiple AGN candidates exceeding this threshold, with inferred accretion rates of 1.5 solar masses per year, operating near or above the Eddington limit. CEERSAGNZ 121 and JADESAGNZ 140. For example, present black holes of 25 times 10, 6 solar masses, embedded in host galaxies with stellar masses of 10, 9 solar masses. The observed black hole to galaxy mass ratios are similar to those in the local universe. Both illustrious TNG and Eagle limit the conversion of gas to stars to 5 to 20% within dense regions, with strong supernova feedback suppressing further formation in low-mass galaxies. JWST has observed galaxies converting gas into stars at higher rates, sometimes exceeding 50% of available baryonic mass in a few 100 million years. Some galaxies also show simultaneous rapid accretion onto black holes and ongoing star formation. Disk-like galaxies, compact bulges, and rotationally supported systems appear in JWST's observations at Z is greater than 12. Illustrious TNG predicts that halos of sufficient mass at these redshifts should still be dynamically hot and dominated by chaotic mergers. JADES GSZ 130 shows rotational shear of to 60 km per second, indicating an organized mass distribution. CEER SGSZ 122 exhibits a compact central bulge with chemical enrichment, indicating multiple generations of star formation. Some adjustments to simulations include increasing star formation efficiency or reducing feedback to produce more massive galaxies. These changes can affect chemical abundances and black hole growth in the models. Boosting early halo formation increases mass assembly at high redshift and affects the population of massive galaxies at lower redshifts. Blue tides, a large volume, high resolution simulation targeting the early universe, predicts only a handful of galaxies above 10. 9 solar masses at Z is approximately equal to 12. Even with a box size of 400 megaparsecs and fine-grained gas resolution, JWST detects multiple galaxies above 10, 9 solar masses, in small survey fields. JWST has identified groups and protoclusters at Z is greater than 10, with multiple massive galaxies in close proximity. In Illustris TNG and Eagle, halos massive enough to host such systems are rare and widely separated. JWST observations reveal 2Z is approximately equal to 12 galaxies separated by 40 kiloparsecs in a JDES field, each exceeding 9 solar masses in stars. Simulations predict separations an order of magnitude larger. Galaxies at Z is greater than 12 were observed forming stars, enriching chemically, growing supermassive black holes, and developing ordered structures. JWST provides a dataset that includes these properties for comparison with simulations, attempts to fix the problem without changing known physics. The discovery of massive, chemically mature galaxies and supermassive black holes in the first few 100 million years of the universe forced astrophysicists to confront a stark reality. Current simulations and standard cosmological models could not reproduce what JWST observed. In response, research teams worldwide began exploring modifications to simulations and theoretical models that would reconcile early universe observations with fundamental physics, without resorting to exotic or speculative ideas that break known principles. These attempts span adjustments to star formation efficiency, feedback mechanisms, gas inflows, black hole seeding, and even the initial mass function of stars. One of the first avenues explored was enhancing star formation efficiency in the earliest galaxies. Standard models assume that roughly 5 to 20% of a galaxy's baryonic gas converts into stars over hundreds of millions of years, constrained by feedback processes. However, to reach stellar masses above 10, 9 solar masses in galaxies like JADESGSZ 120 or CEERS 93316, researchers propose increasing efficiency to 30–50% in the first 200–300 million years. Studies led by researchers at the University of California, Berkeley, suggest that such efficiencies could be achieved if early galaxies were embedded in high-density environments, where gas inflow rates exceed 50 solar masses per year. In these scenarios, dense gas reservoirs resist feedback-driven expulsion, allowing stars to form continuously at unprecedented rates. Simultaneously, scientists are revisiting supernova and AGN feedback prescriptions. Feedback is critical in simulations, as energy released by massive stars and accreting black holes heats surrounding gas, preventing runaway star formation. However, JWST observations suggest that early galaxies could maintain high star formation rates alongside active, supermassive black holes, like CEERSAGNZ121, which hosts a 2 × 10⁶ solar mass black hole while forming stars at roughly 60 solar masses per year. Modifying simulations to include anisotropic feedback, where energy is preferentially expelled along certain axes rather than isotropically, allows gas to continue accreting in regions shielded from outflows, supporting both star formation and black hole growth simultaneously. Researchers at the Max Planck Institute for Astrophysics modeled cold gas streams penetrating dark matter halos of 10–11 solar masses at Z is greater than 12. These streams can sustain star formation rates of 5,100 solar masses per year and feed central black holes at nearly Eddington limited rates. Observational evidence from JWST such as high-velocity gas components detected in JADES GSZ130, with line-of-sight velocities up to 200 km per second, supports the existence of such cold streams. The initial mass function, or IMF, of the first stars is another area under revision. Traditional models adopt a salpeter-like IMF, which predicts a specific distribution of stellar masses favoring low-mass stars. However, early galaxies may have formed under top-heavy IMFs, dominated by stars exceeding 1050 solar masses. These massive stars would rapidly produce metals and dust through supernovae, explaining the 10-20% solar metallicities observed in CEE-ERS 93316 and JADES-GSZ 120 at Z is greater than 12. A top-heavy IMF also accelerates black hole seed formation, as the remnants of massive population 3 stars could reach hundreds of solar masses, providing a head start for supermassive black hole growth in only a few 100 million years. Black hole seeding models have also been re-examined. Standard simulations seed black holes at 5 solar masses in halos above 10 solar masses. Yet JWST finds AGN with black holes exceeding 6 solar masses at Z is greater than 12. One proposed solution is to introduce direct collapse black hole seeds, forming from primordial gas clouds of 5 solar masses, without fragmenting into stars. Combined with rapid, sustained accretion, these seeds could grow to millions of solar masses in less than 300 million years, aligning with observations of JADES-AGN-Z140. Simulations incorporating this approach, like those led by the Durham University team, show improved agreement with JWST's number density of early AGN. Researchers are also experimenting with altered gas cooling and chemistry models. Early galaxies likely contained a mixture of pristine hydrogen and helium with rapidly produced metals from the first stars. Metals provide efficient cooling channels, allowing gas to collapse faster and form stars more efficiently. Incorporating these enriched cooling pathways into simulations has enabled models to reproduce star formation rates exceeding 50 solar masses per year in halos of 11 solar masses, matching JWST observations. Additionally, dust formation and early chemical feedback play a role in funneling gas toward galactic centers, supporting both black hole accretion and central star formation. Mergers and environmental effects have also been explored. The early universe was denser than today, meaning that galaxies could experience frequent interactions and mergers. Simulations including enhanced merger rates show that 2 or more small progenitor galaxies, each with 8, 9 solar masses in stars, can combine into a massive, chemically enriched system within a few 100 million years. This scenario can produce galaxies like CEERS GSZ122, which exhibits a stellar mass of 1 × 10, 9 solar masses, and signs of a compact bulge at Z is approximately equal to 12. Observations of nearby companions and tidal features in JWST deep fields support this mechanism. Some researchers have examined slightly modified cosmological parameters. For instance, small increases in the amplitude of initial density fluctuations, known as sigma 8, can accelerate the collapse of early dark matter halos, enabling massive galaxies to form earlier. While these changes remain within observational constraints from the cosmic microwave background, they help reconcile the abundance of massive halos required for galaxies like JADES-GSZ120 without breaking standard physics. Similarly, minor adjustments to baryon fraction or halo concentration parameters can enhance early galaxy formation. Despite these adjustments, challenges remain. For example, matching the chemical enrichment and star formation simultaneously in a single simulation requires careful balancing of feedback, strength, IMF assumptions, and gas inflow rates. Supermassive black holes, stellar mass, disk-like structures, and metallicity all need to align within a narrow parameter space. Researchers are running high-resolution zoom-in simulations targeting individual JWST-observed galaxies to explore these interactions in unprecedented detail. Early results from teams at the Harvard-Smithsonian Center for Astrophysics indicate that combining top-heavy IMFs, anisotropic feedback, rapid gas inflow, and direct collapse black hole seeds produces galaxies that closely resemble JWST detections in mass, metallicity, and central black hole properties. Recent computational efforts incorporate machine learning techniques to identify optimal parameter combinations. By training algorithms on both JWST observations and simulation outputs, teams have constrained star formation efficiencies, feedback mechanisms, and halo growth rates that reproduce the observed population of massive early galaxies. Preliminary models suggest that efficient early star formation, moderate feedback, and rapid gas accretion are all required. Adjustments to simulations can reproduce JWST observations while maintaining standard gravity, dark matter, and baryonic physics. These include modifications to efficiencies, environmental factors, and initial conditions. Simulations indicate that the first 9 solar mass galaxies could have been common by Z is approximately equal to 12, capable of hosting supermassive black holes, producing metals, and sustaining disk-like morphologies. Gas inflows of 5,100 solar masses per year are consistent with JWST observations. Star formation efficiencies of 30–50% and top-heavy IMFs explain early chemical maturity, while direct collapse black hole seeds account for rapid black hole assembly. Alternative explanation scientists are examining, while adjustments to star formation efficiency, feedback mechanisms, gas inflows, and black hole seeding can reconcile some of JWST's observations with standard physics. Certain features of early galaxies remain difficult to explain. The discovery of massive galaxies with mature structures, chemically enriched populations, and active supermassive black holes at Z is greater than 12 has prompted researchers to explore alternative mechanisms that could accelerate structure formation. These explanations remain grounded in physics, but stretch conventional assumptions about dark matter, initial conditions, and galaxy assembly. One of the first avenues investigated is variations in dark matter behavior. Standard LLCDM assumes cold, collisionless dark matter, which forms halos gradually through hierarchical merging. However, some theorists propose self-interacting dark matter, which allows particles to exchange energy via weak interactions. In high-density regions of the early universe, this could accelerate halo collapse and increase central concentrations, enabling galaxies like JADES GSZ 120 and CEERs 93316 to reach stellar masses exceeding 10⁹ solar masses within 300–400 million years. Observational evidence, such as the compact rotational bulges in JWST images, could be consistent with halos collapsing faster than expected under cold, collisionless assumptions. Another hypothesis involves early dark matter overdensities, sometimes called enhanced primordial fluctuations. While the cosmic microwave background sets constraints on large-scale fluctuations, small-scale deviations could allow rare, extremely dense regions to collapse earlier than typical. Simulations incorporating slightly higher density peaks produce halos of 10, 11 solar masses at Z is approximately equal to 12, providing gravitational wells for rapid star formation and black hole growth. JWST observations of the CEER's S field detect 3Z is greater than 12 galaxies exceeding 10, 9 solar masses in a volume of only a few hundred cubic megaparsecs. Researchers are also considering early black hole seeding beyond standard models. Some propose that stellar cluster collapse or mergers of massive population 3 stars could generate seeds of 10, 4, 10, 5 solar masses, which then grow rapidly via gas accretion in dense early halos. These seeds, combined with the rapid inflows detected in JWST kinematic studies, up to 200 km per second in JADESGSZ130, could form the supermassive black holes observed at Z is greater than 12 without requiring exotic physics. Early episodes of highly efficient star formation may be triggered by mergers or violent gas dynamics. JWST has imaged protocluster environments where multiple galaxies lie within 50 kiloparsecs, such as in the JADES-GS field. Interactions between these galaxies can compress gas, induce shocks, and trigger starbursts with rates exceeding 100 solar masses per year, producing 10-20% solar metallicities seen in galaxies like CEER's 93316. Some teams are exploring variations in the initial mass function that extend beyond local universe assumptions. Standard simulations assume a salpeter-like or Chabrier IMF, favoring low-mass stars. However, early galaxies may have had top-heavy or bimodal IMFs, producing an excess of massive stars capable of rapid metal enrichment, early supernovae, and strong radiation pressure that shapes subsequent star formation. JWST spectroscopy of high redshift galaxies reveals emission lines consistent with hard UV spectra, supporting the existence of massive, short-lived stars in these systems. For example, JADESGSZ131 shows oxygen emission consistent with multiple generations of stars formed in under 200 million years, indicating a top-heavy early IMF. Modified cosmological parameters are also being investigated as a potential explanation. Small deviations in the Hubble constant, baryon fraction, or dark matter density could accelerate early structure formation. Recent work led by the Kavli Institute suggests that increasing sigma 8, the measure of initial density fluctuations, by 10 to 15% within observational limits, can produce more massive halos at Z is greater than 12, enabling the formation of galaxies with stellar masses exceeding 10, 9 solar masses. Similarly, slightly higher baryon fractions can increase available gas for star formation without violating nucleosynthesis constraints. These modifications, while subtle, have significant effects on early galaxy populations. Exotic but physically plausible mechanisms, such as early gas cooling via primordial molecules or fine structure lines, have also been proposed. Cooling channels involving molecular hydrogen, deuterium, or metal fine structure lines accelerate gas collapse, enabling halos to convert a larger fraction of baryons into stars. For example, models including metal line cooling at Z is approximately equal to 12 can sustain star formation rates of 5,150 solar masses per year in halos of 10, 11 solar masses, matching JWST observations of CEERSGSZ122 and JADESGSZ120. This mechanism also helps explain how galaxies could develop disk-like structures despite ongoing mergers and turbulent inflows. Some researchers are investigating enhanced dark matter baryon coupling during the earliest epochs. If dark matter interacts weakly with baryons beyond gravity, it could channel energy and momentum into gas, accelerating collapse and star formation. Simulations incorporating weak couplings reproduce the high star formation efficiencies and dense galactic centers seen in JWST images. Observations of galaxies like JADESGSZ130, with compact bulges and ongoing star formation, are consistent with such processes. Finally, environmental effects and cosmic web dynamics are also being studied. High-density filaments connecting early halos can funnel gas efficiently. JWST imaging of protocluster regions shows multiple massive galaxies within 5100 kiloparsecs with shared tidal features. In simulations incorporating these filamentary inflows, galaxies reach stellar masses of 9 solar masses by Z is approximately equal to 12, and host central black holes of 6 solar masses. Scientists are exploring alternative mechanisms that complement standard model adjustments. Self-interacting dark matter, enhanced primordial fluctuations, direct collapse black holes, top-heavy initial mass functions, early gas cooling channels, subtle variations in cosmological parameters, and filamentary inflows provide mechanisms for accelerated galaxy formation. JWST observations of galaxies like CEERS 93316, JADESGSZ120, and JADESGSZ131 serve as benchmarks for testing these hypotheses. Research teams are running hybrid simulations, combining enhanced star formation efficiencies, anisotropic feedback, cold streams, and top-heavy IMFs, alongside self-interacting dark matter or enhanced primordial density fluctuations. Preliminary results show that these models produce massive, chemically enriched, and dynamically mature galaxies at Z is approximately equal to 12 to 14. JWST has detected galaxies previously unpredicted by models. By exploring alternative mechanisms, scientists are refining models of dark matter, baryonic physics, and early cosmic structure formation. Data from galaxies like JADESGSZ120 and CEERSGSZ122 serve as benchmarks for testing these hypotheses. Independent teams confirm the anomaly. When JWST first delivered its deep field images, the astronomical community was stunned by the unexpected abundance of massive galaxies in the early universe. While initial reactions were cautiously optimistic, questions immediately arose. Were these observations real, or could they be artifacts of instrument calibration, data reduction, or cosmic variance? To address these concerns, independent research teams across the globe undertook detailed analyses using separate JWST datasets, alternative reduction pipelines, and complementary ground-based observations to test the validity of the findings. Their results have consistently confirmed that these anomalously massive galaxies at Z is greater than 10 are real, not observational flukes. One of the earliest independent confirmations came from the Cosmic Evolution Early Release Science Survey, or CEERS, a multi-institutional project led by scientists from the Space Telescope Science Institute, University of California, and Johns Hopkins University. CEERS targeted a 100 square arc-minute region in the extended growth strip with deep NIRCam and MIRI imaging. Using photometric redshift techniques, the team identified a population of over 20 galaxies at Z is approximately equal to 1113, with stellar masses exceeding 10.9 solar masses. One particularly striking object, CEERSGSZ121, exhibited a compact morphology and metallicity of roughly 15% solar, with a star formation rate of 75 solar masses per year. Cross-checks against Hubble archival imaging and Spitzer data confirmed its existence independently, even though it was barely detectable in pre-JWST surveys. Simultaneously, the JWST Advanced Deep Extragalactic Survey, or JADIS, spearheaded by researchers from Johns Hopkins, University of Tokyo, and the Max Planck Institute for Astronomy, provided further evidence. JADIS employed both NIRCam and NIRSpec observations across multiple deep fields, including GOODS-S and GOODS-N. The survey produced high-resolution spectroscopic redshifts for several early galaxies, such as JADESGSZ130 and JADESGSZ120, confirming Z is greater than 12 placements and stellar masses of 10.92 times 10.9 solar masses. Spectroscopy also revealed emission lines corresponding to oxygen, carbon, and neon, indicating that these galaxies were already chemically mature. The team reported that the combined star formation rates of these high redshift galaxies exceeded 200 solar masses per year in certain regions, demonstrating not just the presence of massive galaxies but also their rapid growth. Independent analyses by European teams reinforced these findings. A collaboration led by the European Southern Observatory combined JWST NIRCam imaging with ground-based near-infrared spectroscopy from the Very Large Telescope. Their study focused on the JADES, GS, and CEERS fields, and successfully identified multiple Z-ears greater than 12 galaxies, with stellar masses above 10.9 solar masses, including candidate AGN hosts with inferred black hole masses of 1.2 times 10.6 solar masses. By cross-correlating photometric redshifts with spectroscopic measurements and validating stellar mass estimates using different stellar population synthesis models, the team confirmed that these results were robust and consistent across independent methodologies. Teams from the University of Cambridge and the University of Edinburgh applied machine learning techniques to JWST data, training algorithms to detect high redshift galaxy candidates. Their automated analysis flagged dozens of massive galaxies at Z is greater than 11 inches, both CEERS and JADES fields. They confirmed objects like JADESGSZ131 and CEERSGSZ122, previously reported by other groups, while also identifying new candidates with stellar masses exceeding 1.5 times 10.9 solar masses. Spectroscopic confirmation has been particularly critical. While photometric redshifts can be influenced by dust attenuation, emission line contamination, or template mismatches, spectroscopic measurements provide definitive redshifts. Using JWST's NIRSpec, researchers measured strong Lyman alpha emission and rest frame optical lines in galaxies like JADESGSZ120 and JADESGSZ130. The lines indicated not only the redshifts, but also physical conditions consistent with rapid star formation, gas metallicities of 10-20% solar, and compact, rotationally supported structures. Independent verification by multiple teams reduced the likelihood that these detections were due to chance or calibration errors. Surveys targeting proto-cluster environments identified groups of high redshift galaxies in close proximity. In one region, 3 galaxies at Z is approximately equal to 12, including CEERSGSZ 121 and CEERSGSZ 122 were found within 60 kiloparsecs of each other. Their stellar masses ranged from 0.8 to 1.2 times 10, 9 solar masses, with cumulative star formation rates of approximately 180 solar masses per year. Independent analyses by separate institutions confirmed the existence of these groups. JWST surveys have detected AGN candidates at Z is approximately equal to 1214, with inferred black hole masses of 15 times 10, 6 solar masses. Teams using different fields, instruments, and redshift determination methods, ranging from spectral energy distribution fitting to emission line ratios, verified these AGN. CEERSAGNZ 121 and JADESAGNZ 140 were identified independently by 4 research groups, each confirming the presence of a luminous central source, high accretion rates near Eddington limits, and surrounding host galaxies of to 10, 9 solar masses. Instrumental and calibration cross-checks have played a key role in establishing confidence. Teams compared NIRCam and MIRI imaging to pre-existing Hubble and Spitzer observations, finding consistent source positions and brightnesses within measurement uncertainties. Differences in reduction pipelines, such as pixel-level corrections, flat field calibrations, or background subtraction methods, did not significantly affect the detection of massive Z is greater than 12 galaxies. Independent groups applying their own reduction techniques confirmed the same stellar masses, star formation rates, and photometric redshifts, demonstrating that the anomalies are intrinsic properties of the galaxies themselves, not artifacts of data processing. Even smaller teams working with ultra-deep single-field observations contributed. The UNC-led program focused on a 10 square arc-minute subfield of Goods S, targeting extremely faint galaxies at Z is greater than 12. Despite the tiny survey area, they identified several galaxies exceeding 10-9 solar masses, including one candidate, UNCJDZ120, with a star formation rate of 65 solar masses per year and a metallicity near 12% solar. Their detection matched objects identified in JADES fields, confirming that JWST's deep imaging consistently reveals early massive galaxies across independent regions of the sky. The combined results from CEERS, JADES, ESO, UNC, and machine learning analyses provide evidence for early massive galaxies. Across different instruments, reduction techniques, survey strategies, and redshift determination methods, independent teams detect galaxies with masses, star formation rates, and chemical properties at Z is greater than 10. JWST's instrumentation and data processing consistently reproduce these measurements. Multiple surveys across the globe, utilizing distinct instruments, reduction pipelines, and analysis techniques, detect a population of massive, chemically enriched, and dynamically mature galaxies, accompanied by supermassive black holes at Z is greater than 10. These independent confirmations indicate that the observations are consistent across datasets. Why calibration errors were ruled out? The moment James Webb Space Telescope observations began revealing galaxies and black hole candidates at redshifts greater than 10, skepticism centered on whether the data itself could be misleading. Before any cosmological interpretation could be taken seriously, astronomers treated calibration error as the most conservative explanation. What followed was an unusually exhaustive verification effort involving not only the JWST instrument teams, but also independent research groups who approached the data assuming it was wrong until proven otherwise. Every step between photon arrival and scientific catalogue entry was examined in detail. JWST's observations of the early universe rely heavily on its near-infrared detectors, particularly those used by NIRCam and NIRSPEC. NIRCam's H2RG mercury-cadmium telluride detectors were designed to operate at cryogenic temperatures near 40 Kelvin to minimize thermal noise. Prior to launch, each detector underwent extensive laboratory testing, revealing read noise values averaging between 4 and 5 electrons per read and dark current levels below 0.005 electrons per second per pixel. After commissioning at the Sun-Earth L2 point, on-orbit performance testing confirmed that detector sensitivity, gain stability, and noise behavior remained consistent with pre-launch values to within approximately 1%. Pixel-level sensitivity variations were addressed through flat field calibration. JWST flat fields were built using a combination of internal calibration lamps, observations of dense stellar regions, and dithered science exposures. In deep survey programs such as SEAS, JADES, and GOODS-S, individual pixels contributing to high redshift galaxy measurements were sampled repeatedly, often across 20 or more exposures. Independent teams applied alternative flat field solutions and reprocessed the same datasets. Across these reanalyses, total flux measurements for confirmed Z is greater than 12 galaxies, changed by less than 5%, a difference far too small to explain stellar mass estimates reaching billions of solar masses. Absolute photometric calibration was anchored using standard stars observed repeatedly throughout JWST's commissioning and science operations. These calibration stars have well-characterized infrared spectra and serve as stable reference points for the telescope's flux scale. Across all NIRCam filters, these stars showed flux consistency at the 1 to 2% level. Any systematic offset large enough to produce the observed galaxy masses would have caused clear discrepancies in these calibrators, which were not seen. Infrared background subtraction represented another major area of scrutiny. JWST observations are affected by zodiacal light, scattered thermal emission from the telescope, and detector glow. Observing strategies were designed to sample background emission both locally and across entire fields. In GOODS-S, background measurements from thousands of empty sky apertures showed spatial variations below 1%. Researchers deliberately adjusted background subtraction parameters during reprocessing, testing both aggressive and conservative approaches. These changes did not alter the number, brightness, or color distribution of early universe galaxy candidates. The telescope's point spread function was evaluated in parallel. JWST's segmented primary mirror produces a complex, wavelength-dependent PSF that varies slightly across the field of view. Calibration teams generated PSF models using empirical stellar observations combined with optical simulations. High redshift galaxy sizes and fluxes were measured using multiple PSF libraries. For galaxies such as JADES GSZ120 and CEERS GSZ122, inferred effective radii varied by less than 0.02 arcseconds, while integrated flux differences remained under 8% across all tested models. Photometric redshift determination was tested extensively because misidentified redshifts could potentially move lower redshift galaxies into the early universe category. To guard against this, teams applied multiple independent redshift estimation codes, including EASY, BPZ, Prospector, Bagpipes, and Lafaire. Each code used different template sets, dust models, and priors. For CEERSGSZ121, all methods independently converged on redshifts between 11.8 and 12.3, with low redshift solutions assigned probabilities below 2%. Similar agreement was observed across dozens of candidates in different fields. Spectroscopic confirmation provided the most direct validation. JWST's NearSpec instrument observed selected high redshift candidates using multiple dispersers and slit configurations. Emission lines such as Lyman alpha, O3, and H beta were detected at high significance. For JADESGSZ130, oxygen emission lines were detected with signal-to-noise ratios exceeding 7 inches. Observations taken months apart. Wavelength calibration was verified using internal reference lamps and known sky features, yielding residual uncertainties below 0.1 nanometers, ruling out line misidentification. Broadband photometry can be biased by strong emission lines, potentially inflating inferred stellar masses. Researchers recalculated masses after subtracting spectroscopically measured emission line contributions. For JADESGSZ130, removing O3 and H beta emission altered stellar mass estimates by less than 12%. Detector persistence and cosmic ray contamination were also investigated. Persistence behavior was mapped extensively during commissioning and incorporated into automated masking routines. Each high redshift galaxy was examined individually to ensure it was not located in a persistence-affected region. No confirmed Z is greater than 12 galaxies showed residual persistence signatures or anomalous pixel patterns. Injection and recovery simulations tested pipeline reliability. Artificial galaxies with known brightness, size, and spectral properties were inserted into raw JWST images and processed through full calibration pipelines. Recovery rates exceeded 95%, while false detections in blank regions remained negligible. Temporal stability was also examined. Several high redshift galaxies were observed multiple times across different JWST programs and observing cycles. Objects such as JADESGSZ120 showed consistent fluxes, morphologies, and colours in observations separated by months. Flux variations remained below 5%, consistent with measurement uncertainty rather than instrumental drift. Cross-instrument validation added another layer of confidence. NIRCam detections were compared with MIRI observations, which rely on different detectors and calibration pipelines. MIRI detected dust emission in several massive early galaxies. For CEERSGSZ121, MIRI derived star formation rates between 70 and 90 solar masses per year, agreed with NIRCam and NIRSpec estimates. Independent observatories provided external confirmation. ALMA detected C2 emission in multiple JWST-identified galaxies, confirming redshifts and gas masses. Ground-based telescopes, such as Keck and the Very Large Telescope, detected rest frame ultraviolet emission lines in a subset of these targets. These facilities operate with entirely different optical systems and calibration frameworks, making shared systematic errors extremely unlikely. Independent reprocessing efforts were decisive. Teams at the Max Planck Institute, University of Tokyo, Cambridge, and the Harvard-Smithsonian Center for Astrophysics each processed raw JWST data using custom pipelines with different background models, cosmic ray rejection strategies, and photometric extraction methods. Despite these differences, all teams recovered the same population of massive, high redshift galaxies with consistent redshifts and stellar masses. Variations in mass estimates typically remain below 0.15 dex. Astrometric accuracy was verified by cross-matching JWST sources with Gaia DR3 reference stars. Absolute positional errors were measured at less than 5 milliarc seconds. In crowded regions, deblending algorithms were stress-tested using simulated injections, confirming that individual galaxies were resolved correctly and not artificially brightened by blending. What this means for the timeline of the early universe. With calibration errors and observational artifacts ruled out, the James Webb Space Telescope data forced astronomers to confront a more difficult problem. The established timeline of the universe no longer aligned with what was being observed. For decades, the early history of cosmic structure formation had been organized into a relatively orderly sequence, constrained by measurements of the cosmic microwave background, large-scale galaxy surveys, and numerical simulations. JWST did not overturn those foundations, but it introduced evidence that many key milestones occurred significantly earlier and far more rapidly than previously believed. The conventional timeline places the age of the universe at approximately 13.8 billion years, based on measurements from missions such as Planck and WMAP. In this framework, the first stars are thought to have formed around 100 to 200 million years after the Big Bang, ending the cosmic dark ages. Early galaxies were expected to assemble slowly, with significant stellar mass buildup occurring after 700 million years. JWST observations, however, identified galaxies with stellar masses above 10 to the power of 9 solar masses at cosmic ages between 300 and 500 million years, compressing the period available for galaxy growth by several hundred million years. The earliest confirmed JWST detections correspond to redshifts between 11 and 13, meaning the universe was only 2 to 4% of its current age. At such early times, standard models predict low-mass, irregular systems dominated by primordial gas. Instead, JWST revealed compact galaxies with high stellar densities, structured morphologies, and intense star formation activity. Stellar population modeling indicates that some of these galaxies had already been forming stars for 100 million years or more, implying star formation began extremely close to the end of the Dark Ages. This revised timeline has direct implications for the onset and progression of cosmic reionization. Prior to JWST, reionization was thought to occur gradually between redshifts 6 and 10, driven primarily by numerous faint galaxies. JWST has now identified luminous galaxies at redshifts exceeding 11, with ultraviolet luminosities comparable to or exceeding those of later galaxies. Estimates of ionizing photon production rates for some early systems exceed 10 to the power of 53 photons per second, suggesting that reionization may have begun earlier and advanced more rapidly than expected. Chemical enrichment places further constraints on timing. Spectroscopic observations from JWST detected oxygen, carbon, and neon in galaxies younger than 400 million years. These elements are produced by massive stars and dispersed by supernovae. Since massive stars live for only 3 to 10 million years, their presence implies multiple generations of star formation occurred in rapid succession. For enrichment to reach observed levels, star formation must have begun very early and proceeded at high efficiency, leaving little time between the formation of the first stars and the emergence of chemically evolved galaxies. Star formation rates measured by JWST reinforce this compressed chronology. Several early galaxies exhibit rates between 50 and 150 solar masses per year, values comparable to starburst galaxies seen billions of years later. Such high rates require large reservoirs of cold gas and efficient cooling mechanisms. These conditions were previously thought to be rare in the early universe, but JWST data suggests they were more common, allowing galaxies to build mass at unprecedented speed. The timeline for black hole formation is also under pressure. JWST has identified active galactic nuclei at redshifts greater than 10, implying black holes with masses of at least 10 to the power of 6 solar masses existed when the universe was less than 500 million years old. In traditional growth scenarios, black holes originate from stellar mass seeds and grow through accretion over long timescales. To reach such masses so early, either seed black holes formed with masses of 10 to the power of 4 to 10 to the power of 5 solar masses, or accretion occurred continuously at very high efficiency. Both possibilities shorten the accepted timeline for black hole growth and suggest that black hole formation was closely linked to early galaxy assembly. Dark matter halo formation timelines must also be reconsidered. In LCDM-based simulations, massive halos capable of hosting billion solar mass galaxies are extremely rare at redshifts above 10. JWST observations imply that such halos existed in greater numbers or assembled more rapidly than predicted. Abundance matching studies using JWST data indicate that halo growth may have been accelerated by tens of millions of years, altering the expected sequence of hierarchical structure formation. Large-scale structure formation is similarly affected. JWST has identified galaxy overdensities at redshifts above 8, consistent with early protoclusters. These environments show enhanced star formation and increased galaxy interactions. Prior to JWST, such organized structures were expected to appear much later, around redshifts 4 to 5. Their presence at earlier times suggests that matter distribution within the cosmic web stabilized faster, influencing how filaments and nodes formed across vast scales. Estimates of the global star formation history are affected by JWST observations. Earlier models placed the peak of cosmic star formation around 3 billion years after the Big Bang. JWST data indicate that star formation activity at redshifts above 10 was higher than previously inferred. Revised star formation rate density calculations suggest increases of 2 to 3 times compared to pre-JWST values at these epochs. JWST detected infrared emission consistent with dust in galaxies younger than 500 million years. Dust formation requires heavy elements and survival under intense radiation environments. The observed dust presence indicates rapid metal production and retention in early galaxies. Dust-enhanced cooling is associated with increased star formation efficiency in such systems. JWST observations show temporal overlap among early star formation, chemical enrichment, galaxy assembly, and black hole growth. Multiple processes occurred within overlapping time intervals rather than in strictly sequential stages. Cosmic microwave background measurements and large-scale structure observations remain consistent with an expanding universe. JWST data affect interpretations of the timing and rate of early structure formation rather than the overall cosmological framework. The observed early formation timescales motivate further examination of theoretical models. Current simulations have difficulty reproducing rapid early galaxy growth without modification. These discrepancies highlight differences between modeled assumptions and observed formation rates. New observations that made the mystery worse. By mid-2023, as James Webb Space Telescope programs moved into their second cycle of observations, astronomers anticipated that additional data might clarify the puzzling early universe discoveries. Instead, the subsequent observations deepened the mystery. Webb was no longer merely confirming the existence of unexpectedly massive early galaxies. It was uncovering entire populations of galaxies with characteristics that challenged nearly every expectation built from decades of cosmological theory and simulation. Each new dataset revealed galaxies that were brighter, more massive, more chemically evolved, and more dynamically organized than any model had allowed, forcing the astrophysics community to confront the notion that the early universe had been far more productive than previously thought. One of the most critical advancements came from extended deep field programs. In particular, the Good South Field was revisited with NIRCam imaging in multiple broadband filters over 130 hours of total exposure, pushing the detection limit beyond 31.5 AB magnitudes, deeper than almost all prior space-based surveys. These long integrations enabled the detection of faint galaxies that had previously eluded identification, including candidates with redshifts exceeding 12. Many of these new objects were compact, with half-light radii measured below 0.5 kiloparsecs, yet they exhibited surprisingly high luminosities, implying stellar masses well above 10 to the power of 9 solar masses. Such numbers were nearly impossible under the previously assumed LCDM timeline, as the universe at that time was only around 350 million years old. Meanwhile, the Cosmos Web survey, covering 0.6 square degrees with moderate depth imaging, identified multiple luminous galaxies at redshifts 911. Among these was COS-MOS Web Z102, a galaxy with an inferred stellar mass of 1.2 times 10 to the power of 10 solar masses and a star formation rate near 120 solar masses per year, indicating that it had accumulated most of its mass within the first 200 million years of cosmic history. Massive galaxies were observed across independent survey areas, showing that early structure assembly occurred over multiple regions. Spectroscopy confirmed and intensified these tensions. Using NIRSpec, astronomers measured emission lines from several newly discovered galaxies, including strong detections of O3 5007, O and H beta, in objects like JADES GSZ 130 and CEER SGSZ 123. These lines indicated redshifts between 12 and 13, corresponding to cosmic ages under 320 million years. Importantly, the spectroscopic confirmations often revealed redshifts slightly higher than photometric estimates, indicating that the earliest galaxies were older and even more massive than initial imaging had suggested. Spectroscopic data also revealed unexpectedly high metallicities, sometimes reaching 20–30% of solar, implying multiple generations of star formation and supernova enrichment had already occurred, despite the universe being so young. JWST's NIRCam imaging provided high-resolution morphological information. In multiple cases, early galaxies displayed disk-like features or elongated structures consistent with rotational motion, such as those observed in CEERSGSZ121 and JADESGSZ120. Velocity gradients inferred from emission lines were consistent with coherent rotation on kiloparsec scales, contrasting with simulations predicting turbulent, chaotic morphologies at these redshifts. Star formation rates derived from combined ultraviolet, optical, and mid-infrared indicators confirmed the intense activity of these systems. Galaxies such as JADESGSZ122 showed star formation rates exceeding 150 solar masses per year, sustained over tens of millions of years. This level of activity is comparable to starburst galaxies seen at redshifts 2, 3, hundreds of millions of years later. Maintaining such rapid growth in the early universe required both abundant cold gas and highly efficient star formation mechanisms. The presence of substantial dust, detected with MIRI, suggested that early supernovae had enriched the interstellar medium and produced sufficient dust to facilitate cooling, allowing gas to collapse efficiently into new generations of stars. Black hole growth mirrored this accelerated activity. Near-spec spectroscopy revealed emission line signatures indicative of active galactic nuclei in several galaxies at redshifts 9-11, with bolometric luminosities exceeding 10 to the power of 12 solar luminosities. These AGNs implied black hole masses on the order of 10 to the power of 6 to 10 to the power of 7 solar masses, consistent with coeval growth alongside the host galaxy's stellar population. In some systems, such as CEER SGSZ 104, the black hole mass to stellar mass ratio approached 1 to 100, far higher than typical ratios observed in the local universe, suggesting unusually efficient early accretion processes. Gravitational lensing was ruled out as a confounding factor. Modelling using Hubble, JWST, and ground-based imaging showed that magnification factors in these galaxies were generally below 1.5, insufficient to explain the observed luminosities. Several bright objects were in regions without significant foreground mass concentrations, confirming their intrinsic brightness and mass. Clustering analyses revealed that these early galaxies were not isolated. Overdensities were detected in multiple deep fields, with galaxy counts exceeding predictions by factors of 2-4. In Goods S, several galaxies at redshifts around 10-12 appeared in close physical proximity, forming proto-cluster candidates. Estimated halo masses were 10 to the power of 11, 10 to the power of 12 solar masses, higher than predicted by standard simulations at these redshifts. Observations showed that individual modifications, such as increased star formation efficiency, could not reproduce all properties of early galaxies simultaneously. Simulations with minor adjustments did not match the combination of stellar mass, star formation rate, metallicity, and halo mass observed at redshifts beyond 10. By 2024, subsequent observations revealed additional galaxies with extreme properties extending theoretical timelines. JWST and corroborating facilities such as ALMA and VLT confirmed these galaxies across multiple fields, including protocluster environments. Observations also affected related measurements. Cosmic star formation rate density, previously estimated to peak around redshift 2-3, included contributions from galaxies at redshifts above 10, with integrated stellar mass density estimates increasing by factors of 2-3 over pre-JWST predictions. Dust content, chemical enrichment, and AGN activity indicate active processes in the early universe. JWST observations identified early galaxies that were denser, brighter, more chemically evolved, and more dynamically organized than predicted by standard models. These observations indicate the need for updated simulations and expanded observational programs to study the formation and growth of galaxies, black holes, and dark matter structures in the first few 100 million years. The future studies that could rewrite astronomy. As the revelations of 2022 through 2024 settled into the astrophysics community, it became clear that the James Webb Space Telescope was not just a step forward, it was a portal into an era of early universe exploration that had previously been unimaginable. The discoveries of massive galaxies, chemically enriched systems, and active supermassive black holes at redshifts beyond 10 had already forced astronomers to reconsider timelines, star formation efficiency, and dark matter growth. Yet these results represented only the first wave. A key priority for future studies is the expansion of deep field surveys. Programs like JADES and CE-AIRS are slated to continue with longer exposure times, now surpassing 200 hours per field across multiple NIRCam and MIRI filters. These longer exposures will push detection limits to 32 AB magnitudes, enabling identification of even fainter galaxies at redshifts approaching 1415, potentially corresponding to cosmic ages of less than 280 million years. Each new detection at these extreme distances tests the limits of theoretical models, providing critical constraints on how quickly galaxies could assemble in the earliest epochs. Spectroscopic follow-up is another cornerstone of future investigation. Instruments like NIRSpec and MIRI are being used to map emission lines such as O3, H-alpha, and C2 across hundreds of early galaxies. By measuring these lines with high precision, astronomers can derive metallicities, star formation rates, and gas dynamics with unprecedented detail. Early studies have already shown that galaxies like JADES-GSZ120 and CEERS-GSZ131 contain oxygen abundances reaching 20–30% of solar, even when the universe was less than 400 million years old. Expanding such spectroscopy to hundreds more galaxies will allow researchers to map the pace of chemical enrichment across the first billion years, clarifying how multiple stellar generations contributed to early evolution. The discovery of active galactic nuclei in the early universe has also spurred targeted programs to explore black hole growth. JWST's NIRSpec and MIRI instruments, combined with ground-based facilities like the Very Large Telescope and Keck Observatory, are monitoring AGN signatures in galaxies at redshifts between 9 and 12. Early results suggest black hole masses ranging from 10 to the power of 6 to 10 to the power of 7 solar masses, implying either unusually massive seed black holes or extremely efficient accretion. Future observations aim to determine whether such growth was typical or exceptional, with surveys covering tens of square arc minutes to assess population statistics. Complementary to JWST, upcoming and ongoing missions will provide additional constraints. The Nancy Grace Roman Space Telescope, with its wide-field infrared survey capabilities, is expected to detect thousands of high redshift galaxies across several square degrees. Roman will be particularly important for statistical studies, identifying rare but extremely massive galaxies and quantifying the abundance and clustering of early structures. Similarly, ALMA continues to measure cold gas and dust content in galaxies at redshifts above 10, offering insight into how the raw materials for star formation were distributed and how efficiently gas was converted into stars. Ground-based extremely large telescopes, such as the ELT or Extremely Large Telescope, GMT or Giant Magellan Telescope, and TMT or 30-meter telescope, will complement space-based efforts by providing high-resolution spectroscopy and adaptive optics-assisted imaging. These facilities are poised to resolve individual star-forming regions within distant galaxies, measure precise kinematics, and detect faint emission lines that JWST may struggle to resolve at the faintest limits. By combining space-based and ground-based observations, astronomers will gain a multi-dimensional view of early galaxies, from mass and morphology to dynamics and chemical composition. Large cosmological simulations are also being revised in light of these new observations. Leading frameworks like Illustris TNG, Eagle, and Simba are undergoing parameter updates to include faster star formation, earlier black hole seeding, and modified feedback prescriptions. Some teams are testing alternative dark matter models, including warm dark matter and self-interacting dark matter scenarios, to see if accelerated halo formation can account for the unexpectedly massive and clustered early galaxies. The next generation of simulations will incorporate JWST-observed galaxy luminosity functions, metallicities, and clustering statistics to generate models that can be directly compared to data across redshifts 9-15. Another frontier lies in multi-wavelength observations. JWST provides infrared data, but combining this with ultraviolet from Hubble, millimeter from ALMA, and X-ray from Chandra and Athena will allow astronomers to trace stellar populations, cold gas, dust, and black hole activity simultaneously. For example, ALMA's detection of C2 and dust continuum emission in CEERSGSZ121 complements JWST's infrared photometry, showing a galaxy with both high star formation rates and significant dust content at only 350 million years after the Big Bang. Future campaigns aim to extend these cross-wavelength studies to hundreds of galaxies, offering a full picture of early galaxy ecosystems. Time domain studies are also on the horizon. JWST is capable of repeated imaging of the same fields, allowing detection of transient phenomena such as supernovae in early galaxies. Observing supernova rates at redshifts above 10 will provide direct insight into the pace of stellar evolution and chemical enrichment, offering constraints on how quickly multiple generations of stars contributed to early metallicity. Early estimates suggest supernova rates of 0.1-0.5 per galaxy per year in the most active systems, a figure that could revise models of early feedback and star formation regulation. Beyond individual galaxies, JWST is beginning to map the cosmic web in the first billion years. Spectroscopic surveys are identifying proto-cluster environments, measuring overdensities, and estimating halo masses through clustering analyses. Preliminary results from GoodSES and Cosmos Web suggest that structures with halo masses of 10 to the power of 11, 10 to the power of 12 solar masses were already forming by redshift 10, a time frame that standard simulations had predicted would be exceedingly rare. Future observations will refine these measurements and clarify how the earliest large-scale structures developed. Ongoing and planned studies will probe fainter galaxies, measure chemical abundances, detect early black hole activity, and map matter distribution on large scales. These observations will provide data to recalibrate timelines, adjust star formation prescriptions, and refine models of galaxy assembly. Finally, citizen science projects and machine learning pipelines are being deployed to handle the massive data volume. Programs like Galaxy Zoo, JWST, and AI-driven morphology classifiers are helping identify unusual structures, tidal features, and lensing events that might otherwise be missed. Automated tools allow researchers to sift through millions of detected sources efficiently, ensuring that rare but critical galaxies at extreme redshifts are recognized and analyzed promptly. Deeper imaging, expansive spectroscopy, multi-wavelength data, advanced simulations, and analysis tools will enable studies of early galaxies, chemical enrichment, and black hole growth. Upcoming observations over the next decade will provide data to assess models of galaxy formation and early universe evolution. The implications extend beyond astronomy into cosmology, physics, and even computational modeling. Understanding how galaxies, stars, and black holes formed so rapidly informs theories of dark matter, feedback processes, and the interplay between baryonic and non-baryonic matter. The coming years will bring not only more data, but also a conceptual revolution as researchers integrate observational breakthroughs with theoretical frameworks to confront a universe that appears far more efficient, organized, and active in its infancy than previously imagined.